That's why I just want to double check if we are online. Right, we are online. So just a note to people here in the room, please mute yourself on Zoom and cut your audio speakers off, because otherwise we'll get a horrible feedback. And people on Zoom, please stay muted unless you speak. If you want to ask a question, then raise your hand. And why we are here, because we are at the 12th Gaia Science Others Workshop 2021 and the first ORP time domain workshop. And here in Crete, we gather with a nice group of people who managed to travel to the island, and then the rest of the world was on the Zoom. So welcome to everyone. And I give the floor to Nada Ihanec, who will be chairing today's session.
Thank you. So the first talk is going to be from Lina Tomasela. It's just a note, it's a 5 minutes talk, so 3 minutes plus a few minutes for questions.
Okay, thank you. I present the observational activity carried out by the Italian National Astrophysical Institute, Observatory of Padova, atop of Monte Etna in Asiago. This site is located in the northeast part of Italy, where it is operational the biggest optical telescope in our country, the Copernico 1.8 meter telescope. On its Cassegrain focus, we mount periodically the Asiago faint object spectrograph and camera, AFOSC, for photometry, polarimetry, and low to medium spectroscopy, and the high resolution shell spectrograph around full moon nights. We also host a property instrument such as Aquai, which is a fast photon counter. The Copernico telescope is operated remotely. Close to Copernico, you see in this picture, there is a 1 square degree fields Schmidt telescope, which is fully operated in robotic mode from a couple of years. Environmental conditions. The alpine climate in Asiago is sometimes rainy or snowy, but likely the best period for observation is in the winter time, when we have long nights with average seeing around 1.5 to AXEC. Those are open for observation, at least partially, between 50 and 65% of the nights. And maintenance is done during the springtime, because this is the rainy period in Asiago, that is in May and June. This slide is about our telescope time organization. In order to compensate for bad weather and to maximize science, overabundant telescope time is assigned only to a limited number of large projects, which last 2 years with a call for proposal. The PIs of large programs are generally staff researchers in the Padova Observatory. However, these programs are usually part of bigger national or international collaborations such as Gravita, Engrave, IPESTO, NATS, WAVE, and so on. Prompt TO submission or also telescope rescheduling is always possible for sudden events, for example, gamma ray burst, alert, gravitational trigger, or golden neutrino trigger. Currently, all the approved large programs in Asiago are related to time domain astronomy. For example, spectroscopy of asteroids, transit timing analysis of exoplanets, monitoring of novae, symbiotic stars, spectroscopic binaries, AGNs, variability, and in particular, classification and follow-up of supernovae and intermediate luminosity transient. This last project is conducted by Padova Asiago Supernova Group. It is a long-lasting program aimed to the early classification of extragalactic transients and the selection of interesting candidates for which we start a high-cadence spectrophotometric follow-up. In this slide, I resume the scientific production with Asiago telescopes. The graph at the top shows the number per years of ATES, GCM, astronauts coming from the Asiago classification program. Actually, a fraction of these classifications regards the Gaia transients. In particular, in 2014, we joined the Gaia Science Alerts Working Group to contribute to the validation of the transients alerts from Gaia with a dedicated observational project. The graph below shows the annual number of referee papers, partially or totally based on data collected with the Copernicus telescope, which is in red, as compared to the scientific production of other similar class telescopes. On the right, there are the papers which include our contribution for the follow-up of selected Gaia transients. And finally, I conclude showing the distribution of Asiago referee papers subdivided per instrument with the aim to underline the remarkable increase of productivity for Schmidt telescope after the implementation of the robotic mode a couple of years ago. Now we are working for the robotization of Copernicus 2. This will allow us to obtain not only photometry with Schmidt, but also photometry and spectroscopy in robotic mode with Copernicus. And we hope to sensibly increase our data collecting efficiency, especially in time domain astronomy activities, hopefully also for Gaia alerts. And thank you very much.
Thank you, Lina, for the great talk. Unfortunately, due to time, if anyone has any questions, please write in Slack. So, the next speaker is Michel Denneveld. If you can please share the screen, and you have 10 minutes or 12 with a few minutes for questions.
Yes, do you see my screen?
Yes.
Okay, let's try if it works in diapositive mode. No, okay. So
So right now it's good. Yes.
This way.
Great.
Yes.
Perfect.
Okay,
Yes.
so I will talk about follow-up of some Gaia alerts. But before, I would like just to make a small comment. Today we are the 11th of November, which is a holiday in France and in some other countries, because we are celebrating the end of the First World War. And I'm happy to see that European collaboration is progressing instead of continuous fights as we had in the past. So thanks to Opticon and ORP for helping into that. So I will talk about classification of older Gaia objects and specify recent alerts we have been following up. This is the slide I showed you last year when we had compared Gaia alerts with archive spectra from Sloan Digital Survey and LAMOST, and we had about 20 cataclysmic variables, 200 galaxies, 100 QSOs where we found archive spectra, and among them we identified 10 new changing look quasars. Now I will show you that in the last year we have been progressing, and we have been identifying now over 50 new changing look quasars, and I will show you a few examples. So the one question is that, of course, to follow up, because there are so many candidates, we are heavily relying on Gaia comments. And so sometimes I worry if the comment depends on whom is on duty, because sometimes during weeks we see no AGN, no quasar, and then suddenly for 1 week a lot of young stellar objects, and then nothing during the next months. So maybe Simon can clarify a bit that. And of course, if the BP-RP spectra would be at least corrected for the spectral response, that would help a lot in selecting the objects. So we are mainly doing the follow-up at the moment with 2-meter class telescopes, essentially at the Nordic Optical Telescope, and now also at Haute-Provence, which I will show in a few moments. But the main problem is that the spectral date is usually different from the alert date, and we should try to minimize the delay to understand what is going on. And of course, it's crucial to select, to reduce the number of selection in view of what is coming with the LSST in the future. Sorry, there are a lot of slides which are not hidden because I'm not in the presentation mode. So one example here is Gaia 17 boom, where we had 3 Lamost spectra in end of 2015, which in the Gaia curve are this red point, and you see that the spectra were taken just before the rays of the object, and apparently in this case the broad Balmer component here and the magnesium 2 had increased before the photometric increase, but because the light curve is a bit scarce, it's difficult to say. And we have obtained a recent spectrum 2 months ago, which corresponds to this highest point here, and so the spectrum looks again like the blue one. So we have to wait that the object goes down again and see what is happening after that. So some example of QSO variations. At the top, you have random variations, which are classical, which are believed to be due to change in accretions. But at the bottom, you see 2 long-term variations, which are not understood. We have to see what is changing there. The light curve is not enough or is too late. On the left, you have an object which is 21Bij, which we missed. So we don't know whether that's a supernova or a burst, whatever. On the right, you have another one we are following, and hopefully this one will get the spectrum before it goes down again. It's a recent 1 magnitude increase in the Seyfert-1 galaxy. More examples. These are the ones we are most interested in. Smooth, long-term variations. But of course, we select them when they are going up because it's easier for the telescope, but we should also pay attention to some which are going down, like the ones at the bottom, to see whether the reverse change is happening. Usually when they go up, we see a change, increasing of the broad component, increase of the blue continuum, and now we have to check when they go down if these features disappear again. In the lower right, unfortunately, this is one interesting case, but we have missed it at the moment to get the spectrum. Some examples here, you have 21BHR going up. The reference SDSS spectrum is a liner spectrum. And at the bottom, you see the recent spectrum where the broad component has considerably increased. Another example where the broad component has increased. Now, this one is interesting because it's going down now, so we'll get a new spectrum to see if the broad component disappears again. Other examples, this one has been followed several times. Broad component appearing together with the blue continuum, and we have to see what is happening now that it's going down again. While other examples. Now, let me put this one off because, yes, physics of AGN, the unified models, which you are schematized on the right, suggest that you have an obscuring torus. If you look outside the obscuring torus, you see a Seyfert-1, and if you look through the torus, you see a Seyfert-2, that is, you don't see the broad line region nor the active nucleus in the center. And here is radio loud if you see the jet, and on the bottom radio quiet if you don't see the jet. But the problem is a change from 1 to 2, as we see in the AGNs I showed you before, cannot be explained by change of viewing angle and cannot work with a compact torus. So either you have moving holes in the torus or a stop of the accretion in the central engine. And so we have to measure timescales. And I show you this. Recent models by the Mexican group have shown these are 4 examples of known Seyfert-1 galaxies. And you see that you have, in fact, different types in existing Seyferts which have been studied in detail. The gray part is the gas, which you see in the X-ray. The brown part is the dust, which is either homogeneous, like here, or clumpy, like on the top. And the bottom one is the classical view of the Seyfert-1 galaxies, where you see outside the clumpy torus. But you see the top model is, in fact, also the same as you would use for a Seyfert-2 galaxy, yet they have a Seyfert-1, which modeling follows that. So clearly we have to go along those lines and found the time scales of variations, which would give you, say, the size of the holes or the distance between the clumps to have the time scale of variations. So this is the way we want to go. What is happening? Yes. So follow-up. It's not that. Any telescope of 2 meter class like NOT, Asiago, Haute-Provence, etc., And in Haute-Provence now we have a new spectral imager which is under test. It's a modified copy of the Sprat Liverpool. It's hanging at the folded Cassegrain of the 1.9. And we thank the colleagues from Liverpool who helped in setting up the design. But as you will see in the next slide, it's not so easy to copy simply a spectrograph from one telescope to the next. This instrument is now available for general use as of the end of this year and will be opened for target of opportunities from April next year on. So here is the mechanical design. You have a slot with 3 possible gratings, which are VPH gratings. At the moment, there are only 2 in. The range is either blue, 4,000, 8,000, or red, 6,000, 10,000, and a deep depletion CCD. The schematics here is the right part is the spectrograph on itself, but because the Sprat Liverpool was opened at f10 while OHP is at f15, we had to introduce a focal reducer in front, and of course this is additional optics, which is not helping for transparency. The resolution is typically 700 at 6,000 angstrom. Maximum efficiency is only around 20%, and of course, as the seeing is quite variable, whether you get the whole flux in the slits or not changes a lot what you can do. What we need is to get a better objective because we have just used custom available objectives, which are not excellent, but it's 50,000 euros, which we don't have at the moment. So if there can be help from Opticon or ORP, that might be nice. Here you have on the top a first spectrum during test in the red part earlier this year, a T Tauri star. We have H alpha here, and you see the calcium infrared triplet there. And this is the efficiency curve I've measured last month in the blue setting. You see it peaks around 7,000, but rapidly goes down towards the blue because of the objective is not optimal. So I'll show you an example of NOVA CAS 2021. It was discovered on March 18. It's still bright today, 8 magnitude, so a lot of telescope can follow up, and it's easy to observe because it's circumpolar. The interesting point is that it was said to be perhaps coincident with the WUMR eclipsing binary existing before. So we have to wait for evolution. What we are interested in is to see abundances in the nebular phase and eventually find the companion when the nova has gone down completely. Here at the top, you have a red spectrum obtained at OHP. You have the H alpha here. That was early in spring, and you see the Paschen lines in emission. And the Gaia, it has been detected by Gaia as I don't remember 21 BPE. Interesting in this light curve is that effectively there is an object which was detected there before, and so the Gaia light curve is very useful to find a previous companion. And now I'll just show you a spectrum which was obtained last month. This is in the blue part. You have again H alpha here, but because the continuum seems to go up quite rapidly, H alpha is squeezed down in the scale. But you see, you still have a small P Cygni profile, which means that the envelope is not fully optically thin. And by the way, at OHP, we have also observed and classified a few novae in M31. So my conclusion is clearly you see there's a lot to do and we need a lot of spectroscopic time. So some coordination among the telescopes which are able to follow up would be good, for instance, with Asiago and with the NOT, that we coordinate which object is observed where and get a better light curve. We need to react rapidly, but not as rapidly as for GRVs or supernovae. For AGNs and even novae, days is perfectly adapted. And for instance, we need to distinguish a tidal disruption event from AGN activity, so the follow-up is needed. And the Gaia light curves are effectively very welcome because they provide long-term light curves as long as the selection is well-defined. And I want to thank Simon and his alert team for superb work, which helped us a lot. Thank you.
Thank you. And it's perfectly on time, so we have time for questions. Anyone? So yeah, Lukasz, please.
Hi, Michelle. I just have a quick comment. You mentioned that the AGNs you observed from Gaia was, by the way, this is beautiful data set and really worth exploring scientifically. But the comment I have is that from what Simon said on Monday, the comments will not be generated anymore because, as you also noticed, they are generated by humans who have different moods and sometimes they comment it's an AGN, sometimes not. So they will not be there anymore starting next year. So it would be anyway a good idea to establish new ways of identifying AGNs.
Yes.
It should be easy, but yeah.
At least, if not a human comment, if you can put in whether it is coinciding or not with a previously known cipher, that would help, and that can be done automatically, I guess.
Well, yes, it's doable. It's essentially, it's quite simple, but we have to talk about this. So I'm happy to cooperate on this.
Yeah, because you see, there are so many targets, we cannot follow up most of them, so the selection needs to be helped in some way.
Exactly. Okay, thank you.
Then we have a question from Maya. You can unmute yourself, please. Ask. No, sorry, not unmute yourself, but
No.
You have to come
yes,
closer.
please. Yeah, I was searching where you are.
Yes, hello, very interesting talk. And I have a question. You have showed a very fast outburst of AGNs happening. And I wonder, is it possible with our current technology to react to those, or we have to just accept we will always be a little bit too late for those because they are so fast? I don't know if that makes sense, but...
Sorry, there is a lot of echo in the room, so I didn't get your question exactly.
Okay, I wrote that on Zoom chat. Maybe that's easier. So we can...
Okay, thank you. Sorry for that.
Yes, okay. Yes, Simon, the last question, quick one, hopefully.
Okay, thank you, Michelle. That's really nice. I was just looking to try and find the parallax for the progenitor of Nova Cas. So I'll do that offline, but as we find more and more of these, the parallaxes should be extremely helpful, shouldn't they?
Yes, certainly. And what we have to see now is if the evolution in the spectrum is because we see the white dwarf itself or because we start to see the companion. That I don't know yet. Yes.
Yeah. And very good point about the lack of comments and the help for filtering AGN, flagging AGN. So we'll have to make sure we include some more auxiliary information to help you with that.
Yes, thanks. A lot.
So I'll talk to you more about that, Michelle, offline.
Yeah,
thank you.
Thank you. Yeah, as I said, we have more than 50 good candidates now where we have a first epoch spectrum follow-up and we are waiting for further evolution.
Great, yes, really interesting work. And for any additional questions, please, if you can ask on Slack. So now we continue with Marco Lam. I think he shared the slides. And you have 12 minutes and 3 minutes for questions.
Okay, yeah, thank you.
Okay.
Yeah, great. Yeah, thank you for having me here in this workshop again. Yeah, today I'm going to talk about the spectral data reduction toolkit, the Aspired, that I have been developing in the last 3 years. So many people in the audience have heard of it in the past already, but please bear with me, there's something new towards the end. Yeah, and here are all the names of the people that have made this project possible, and of course the funding bodies as well, and particularly the flexibility and opportunity given by various people over the difficult time since the beginning of 2020 was really, really much appreciated to let me continue on this work. So in this talk, I'll quickly go through the background and the motivation of this work. And then I will move on to the toolkit itself. And towards the end, I will talk about the current status and the future outlook of this project. So this software development was originally part of the development of a portable instrument and pipeline with the Liverpool telescope, which is now the spectrograph, and originally funded by the then Opticon, and then carry on, and then the work carry on through different grants, and now I'm based at the Tel Aviv University and using the ERC research grant from Yair Akafi to continue on this work. So this software was originally designed to do the data reduction for the original spread data. But at the same time, in view of the IRAF being no longer officially supported, the Liverpool telescope, as well as the Warsaw University, was a joint project, and they were thinking about building a portable pipeline and software together at the same time, because when building a dedicated pipeline for a specific instrument on a telescope takes a long time and takes a lot of staff effort. So the idea is to build something that is relatively portable, so only minor adjustments that will be needed in order to apply one pipeline to another, to apply an instrument from one telescope to another. So by having these, they will facilitate rapid science output and allow many cross-platform and interactivity between observatories, between users, and also the data delivery can also be more modern and interactive. So moving on to the toolkit itself, so I categorize the spectral data reduction itself into roughly 7 steps. So it is from the spectral image that we have to start tracing the spectrum on the image, and then perhaps need to rectify the image to make them into the right shape, and then to extract them, and then do all other higher level calibrations from there on. So the software is to provide some simple functions for you to execute in order to perform all these operations. So starting with the trace identification, for some simple form of instrument, and by simple I mean with a single detector and also with a single prism or grism, instead of having some very fancy dispersion mechanism. A simple function call would be possible to find the trace or traces on the 2D spectral image. For example, on the right here, you see this highly tilted spectrum. The trace function here will automatically identify the trace across the entire frame and then do some cross correlation and within the frame itself in order to find the shift of this spectrum across the dispersion direction. And then next, if your spectrum, for example, this one is taken from the LCO Floyd spectrograph, it has a highly curved and tilted spectrum. What we have to do is to correct them in both directions, both the dispersion and the spatial directions, before we can perform any spectral extraction. Again, this only requires a single function call. So after rectifying the image, then we can extract the spectrum. So these are all very standard procedure. So between the red line that is a 2D spectral image. And then in the green region here and there, they are the sky. They are the regions used for sky estimation, so that you can subtract the sky background from the source itself. And there are various ways of weighting that you can use in order to get some optimal or simple expressions. Built in, I have provided 3 different methods for this kind of extraction, and you can see the comparison of the extracted spectrum from the 3 methods and the noise in comparison among the 3 of them. Again, this can be done with a single function call. And then moving on to the higher order calibrations, the wavelength calibration is powered by another software, which is in concurrent development by my colleagues. And it is aiming to provide an as automated reduction as possible, but it is really difficult. So what we can achieve now is, if you have a good set of lines in the wavelengths, and that is roughly matching to the lines that can usually be detected from the arc lamp image, then the automation will almost always succeed in matching, giving a good wavelength calibration. Otherwise, they can home into some other local minima and giving some bad calibration. And after wavelength calibration, we can perform the flux calibration, which is essentially dividing the electron counts extracted from the spectrum to the literature values. And then we can generate the sensitivity function, the black line here, based on the division between the 2 other lines here. And then using this function, we can apply to the observed spectrum to perform the flux calibration. And then the last 2 are the atmospheric extinction correction and the telluric absorption correction. These are the new functions that were not available in the past. So built in, there are 4 different extinction correction functions. They were taken from the 4 different observatories. And the reason they are there is because those are the only extinction curve that I can find online publicly. So I just put them all in here. But you can see that they're all very similar. So if you're not really counting every single photon, then it shouldn't really matter that much. Then there's also a highly experimental function, which is the telluric absorption correction function. As you can see from the gray curves here, these are the telluric profile that is being identified from the stage of the flux calibration when masking over these telluric region. And then when doing the sensitivity curve generation, we have to take into account of these extra absorption features. And then by doing other minimization function, then we can find the best absorption correction weighting, and when applying to the actual science target calibration. So in terms of the software development itself, it is entirely written in Python, and there is absolutely no component of IRAF, and it does not depend on any libraries from Starlink, which can be quite difficult to install at times. And the project management itself is almost entirely done on GitHub, including all the different versioning and other bug or feature request tracking. Because GitHub is a really well-developed web tool. It provides a function called the GitHub Actions. What it does is, every time when I am trying to update my source code to GitHub, it will trigger some build test and unit tests. So every time it will know that I haven't broken everything, and it will also automatically check for external dependencies if in case some version increment from other software would be suitable for my software. And it will also automatically upload to the Python package index so that users can do pip install aspire with a single command and can get it installed. And GitHub will also update the documentation automatically after any code changes, any API changes. And the interactivity of the software is entirely powered by Plotly, which can provide interactive plots in a browser, as well as saving them in static plots. So as of last week, the version 0.4.1 was released, and we are now waiting to hear back from various users before setting plan in a future version. And some of the most important thing that will certainly be included in version 0.5 is that we have to continue to improve the quality and usability of the extinction and telluric absorption correction. And hopefully we can add a better plotting library and also more commonly used by Python user, which is the matplotlib, and also the interactivity support. And more diagnostic plots would be useful as well, but we would like to hear more from the users before deciding on what kind of plots would actually be useful. And currently, it is a candidate software to power the pipelines at these facilities, and it is also unofficially tested with various spectrographs. So if you would like to find out more or test the software itself, I would strongly encourage you to go to the GitHub page, this one here, and it will have, it contains all the links to all the other links I have put down here. And also for the archive article, it was also uploaded last week. It is not peer reviewed, and I'm waiting for the peer review process when I am confident enough to release the software as version 1 publicly. Yeah, so that is all I would like to talk about. Thank you very much.
Thank you, Marco. This is really amazing software that you created, but unfortunately we're out of time. So all the questions, if you have them, please write on Slack. Yeah. So the next speaker is Justas Zdanovicius. Sorry. So please, if you can share the slides, and I will tell you when you have to. At the time of 10 minutes, I will wait. So.
Where do you start? Okay. I talk a little bit about our observation at the Moretti Astronomical Observatory. We participate in that project of hunting black holes.
Full screen mode.
Yes, I think it's not that mode.
You must go back. Yeah, escape from this. No, go to the presentation. Oh yeah, you are right.
Share screen.
And select the full full screen and not only one.
Maybe here.
Yes. Yes, that's complete.
This is our group at your telescope. And we already know, it's not easy to find it. Vitas, I, Marius, and Erika Druta. And our telescope is in the center of Europe. We were not very good, but our telescope was operating from Vilnius. And if we see some gaps between clouds, we can observe just few hours in one night. And for Gaia alerts follow, and it's sometimes enough. In observatory, we have 3 domes, and we usually use the smallest telescope. It is thermoelectrically cooled CCD camera. It is enough to start cooling half an hour before the observation. We can open the roof from Vilnius, and no necessary to be some people at telescope. Not in the evening or in the morning or all night. It's operate just from Vilnius. We can operate from the telescope. And during the last year, we observed more than 20 targets from Gaia alerts. Oh, I don't fit Gaia alerts in the beginning of all alerts. And our telescope not so crowded by program. And like in that case, there was Gaia alert, and we don't know if we need to follow that star or not. And don't wait the next Gaia point. We can few weeks just following that star and look if what is going with that star. It increasing, decreasing brightness of that star, and decide if we need to follow this object or no. And in that case, I think we don't need to follow the star more, but we can use for that. In some cases, we following the star more time, but because our gain was looking for lensing event, in that case that I showing, I think it wasn't micro lensing event. This alerts in black hole dome has a big priority, but I think we decide not follow more that star. And our main target in the last few years was Gaia 19 DKE. And in that curve, we have more than 1,000 points. It was very nice follow-up. Also did in Molėtai Observatory. We have many points successfully. We also following some other stars like Gaia 21 EFS, and we managed just to have some points in the directly in the peak in I, R, and V bands. I think that point is from Molėtai Observatory. given, and we are very proud of that. Another star that is following is Gaia 20Y-DNC. And also we have quite nice following and nice light curve from molecular data. Also we try following that star. In some cases, if a star was not so bright because our telescope not very big, we use just the few red filter. For example, in that case, we follow it only with I and A band, because in V band or B, it is the star was too faint this time. Now I start with the following, and we don't know what it is exactly. This is Gaia 20BOR. And we looked, because as I understand, nobody was interested in that star. We looked what can be the star. We find in the catalog, Star Course catalog, we find that reddening was 2.3 magnitude, but temperature effective is 1100 Kelvin. Also, their rear free also takes quite long distance, and using this data, we pointing that star in HR diagram. It is here, late type B star, and Erica try examining the data from that star that he has from TESS. And he downloaded TESS data. He did the analysis of that curve, found some period, but we saw that it is variable in magnitude not so big, and this variation can explain the peak in the light curve that we found for that star. For us, will be we are very interesting that someone use that data, and we will know what is really caused that peak in that star. And also our acknowledgements that because our project is part of the research project Polish Lithuanian Black Hole Hunt, was following grant from the Polish National Science Center and Dina grant, and the Lithuanian also from Research Council, and it is all. Thank you for attention. That he joined the other group to his work.
Yeah, thank you for a great talk. Do we have any questions? Maybe first from the room or on Zoom. We have time for questions.
I wanted to ask Gaia, well, I like the lighters, the ones you showed in 21DNC. It's definitely micronizing, but the Bohr, 20 Bohr, it looks like micronizing, but it's clearly some kind of impostor, micronizing impostor. But then 21ECY drew my attention because it looks a bit unusual, so we have to look at this. together later.
Okay.
But I guess this is the great part of Decalton, right? That even if one group doesn't like the target, then the data is still being observed and produced, so that everyone can share. So great. Yeah. Any more? Pavel, I see you.
May I?
Please.
Yeah, regarding Gaia 20 BOR, which we call Boromir, we got already low resolution spectra from Nariman Ismailov team from Azerbaijan, Shamaki Observatory, as well as from Liverpool Telescope Sprat spectrograph. But we are confused because there, in one spectrum, we see some emission in H alpha, but in the other spectrum, we don't have such a clear emission. So that's why we don't know what is it, and the light curve is suspiciously similar to the light curve of typical microlensing event. So that's why we need some other confirmation of the nature of this target. That was just a remark.
Thank you. Anyone else? No? So for any extra questions, please write them on Slack or Zoom, but on Zoom they will disappear. So, okay, we can move to the next speaker, Adam Kalash. As you're here and the cat disappeared.
Yeah.
And okay.
You all can see my slides?
Yes.
Okay, great. So hello everyone. My name's Adam Kawash. I'm a PhD candidate at Michigan State University, and my thesis is focused on estimating the galactic nova rate. And today I'll be talking about how Gaia has been a really great tool in trying to accomplish this goal. So people have been making estimates about the total frequency that classical novae are produced in the Milky Way for almost 90 years now. So I'm showing here predictions for the Milky Way's classical nova production as a function of the year that they were published. So these early rates in the 30s, 40s, up to the 1980s were really done with small samples of galactic novae. So you can see there's a large variance in them, as low as 50 and as high as 260 per year. And then in the 90s and early 2000s, we used a little bit larger samples of galactic novae and started to look at study novae in other galaxies like M31 to try to compare that to the rate in our own. And these predictions were a little bit lower in the 20s and 30s per year. And then lately the rates have increased a bit, sort of converging around 50 per year. And this is the number that most people quote now, is that we think the nova rate in the Milky Way is about 50. But the only problem with this is we don't find 50 per year. We don't really find even close to 50 per year. So if I show down here, the blue histogram, the number that we discovered in that year, it's definitely increased recently, but we're kind of averaging a little over 10 per year. So we don't have a good explanation for this discrepancy between the discovered rate of around 10 and the predicted rate of around 50. We don't have an answer for why we're only discovering 20% of the galactic novae. And I think Gaia can help us understand this. So first, Gaia finds and reports classical novae. So we can bump up these numbers down here. Plus we can use Gaia's well-defined scanning law. We can do a completeness study in Gaia to figure out what percent of classical novae we think we're recovering in the galaxy to make our own prediction. So we can put our own point on this plot from Gaia observations. So why is Gaia good at doing both of those things? So for finding novae, Gaia is the only survey that observes the whole sky with a red filter. So other people have mentioned this week that Gaia isn't afraid of the galactic plane. And that's the reason Gaia is really good at finding classical novae. So Assassin isn't afraid of the plane either. They observe the whole sky, but they use a very blue filter. So they can't see far into the dust in the galactic plane, like Gaia's broad filter makes them able to see further into the plane. So Gattini is an infrared survey looking for transients, and they find classical novae too, but they're only in the northern hemisphere, so they can't see the southern galactic plane, and they can't really see the bulge for about half the year. So there really are a lot of novae that only Gaia finds. And then second, we can use Gaia to make our own predictions. So we can make a model of galactic novae. We can put those into Gaia data to figure out what percent we're recovering. If it's only 20%, then we'll make a consistent prediction with the previous papers that the nova rate is 50, but we can find that value doing analysis of Gaia's data. So what do novae look like in Gaia data when they're reported? So this is an example of a nova, Gaia 19 DUM, which was nicknamed Dumbledore. And there's a few things on this page that really give away that it is a classical nova even before it's spectroscopically confirmed. So I want to point those out. So first, its position. So it's in the galactic plane. So its latitude is 0.3 degrees. So it's galactic and it's not necessarily nearby. Second, it was noted that it has a high amplitude. So this is consistent with classical novae. They're very bright. They brighten by many magnitudes between quiescence and their peak brightness. This helps differentiate between low amplitude events, like say a dwarf nova or a microlensing event. Then if you look at the light curve, it was discovered in 2019, but it was detected all throughout 2020. And novae can be very fast. They can fade very quickly, but if something like this is lasting a long time, it's not a dwarf nova or another type of cataclysmic variable outburst. Really only novae last this long. And then last, and I'd say most important, if you look at its BP-RP spectrum, it's very red. So there's not a lot of flux in the blue filter, but there's a ton of flux in the red filter. So either this transient is intrinsically red or it's reddened by a ton of dust. And because this thing is a nova, it's the latter, that it's far away, it's bright, but it's far away. So it's really red from dust extinction. And I'll just note that novae don't have to be red like this. If they're nearby, if they're off the plane, they're not going to be this red, but amateur astronomers are really good at finding the nearby close, bright blue classical novae, but Gaia and Gatine are sort of the only surveys that are sensitive to these red transients. And that's why Gaia is so good at finding these. So about August this year, my group at Michigan State got really interested in using Gaia to find classical novae and to estimate the galactic nova rate. And our first question was, are we confirming all the galactic novae that Gaia detects and reports? So I know Simon showed these figures on Monday, but I want to show them again because they're really important for what I'm talking about. If you look at where Gaia is reporting transients compared to other surveys, so Gaia and Assassin here are all sky, but there's this huge density of transients in the galactic plane that Gaia has that Assassin does not. And this is again because of the red filter that Gaia uses versus the blue filter that Assassin uses. Gaia can see further into the plane. And I'm sure the finer pixel scale of Gaia doesn't hurt either, looking in crowded fields in the plane. And then if you look at where we're classifying transients versus where the transients that are left unclassified, there's a huge number of unclassified transients in the plane. And this is where classical novae should be. So this is suggesting to us, no, we're not confirming all the classical novae that Gaia reports. We need to do a better job. We need to look at Gaia transients more closely. So what we did is we looked at all the alerts that Gaia has ever reported. At the time, it was over 17,000. Luckily, we don't have to look at all of the pages of all 17,000. We can do things to rule out transients that are not classical novae. So the reddened ones that we're missing are only going to be in the plane. So we can rule off things off the plane, like a few degrees. We can also rule out low amplitude events. Classical novae brighten by at least 5 or 6 magnitudes between quiescence and when they're detected at peak. So we can rule out low amplitude events. And that brings the numbers down to a few hundred, and that's more manageable to look through. So we looked through them and we picked out about 10 that really look like other classical novae that were confirmed that were just never followed up. So here's an example of 6 of those. You can see the light curves are detected many times, sometimes for years. They're all very, very red. And because these are all in the plane, they're probably reddened by dust. So there's not really a lot of things that these could be besides classical novae. But we had a campaign with our time on the SOAR telescope to follow these up spectroscopically. And we posted a few ATELs this year telling our results. And we were able to confirm 5 of these already. Even though some of these went off years ago, we were able to see emission lines that are consistent with past classical nova eruptions. 4 of them, we didn't see any emission lines or continuum. The transient was just too faint. Maybe it was a classical nova, maybe it wasn't, but we just got there too late. And then we've also been checking Gaia transients more closely this year, and this has led to more classical novae confirmed this year. So if I show you how many novae Gaia detect, or how many novae that we follow up from Gaia, this is that for the past since 2018. These error bars here are the ones that we were not able to spectroscopically confirm, but the alerts still look like classical novae. So this kind of gives you an idea of the upper bound of how many novae Gaia has been finding over the past few years. And this is compared to the total number that was confirmed that year. So if you look at this year, we've confirmed 17, and this is the most we've ever confirmed. And that really is because of Gaia. There's been 6 novae this year that only Gaia has detected. So they're too faint and red for assassin or amateur astronomers to find. They're too far south for Gattini, and this really only leaves Gaia to find these classical novae for us to follow up. And it's no doubt that that's the reason that this has been the year that we've confirmed the most. So now that we have a better idea of how many transients or classical novae Gaia is detecting, we can do a completeness study in Gaia data. So what we're going to do is we're going to make a model galaxy of novae. We're going to put them into Gaia data, and then we're going to try to calculate what fraction we're recovering. So this slide's really crowded. I'm sorry about that. I'm kind of condensing an entire paper into one slide in the interest of time. But if you want to know more about our galactic nova model, you can read our paper from this year. So what we're doing is we're distributing novae in a galaxy. To do that, we're just assuming that the novae are going to follow the stars in a galaxy. So we use stellar density maps of the Milky Way to distribute the novae. This is what that looks like for 1,000 novae in galactic coordinates. So most novae are towards the galactic center in the galactic plane. We can give them an absolute magnitude, which we know for classical novae pretty well from looking at novae in M31 with well-defined distances. All right, once we have their positions and distances, we can calculate their extinction based on 3-dimensional dust maps of the Milky Way. So we use this MW dust map from Joe Bovey, who stitched together different 3-dimensional dust maps to make an all sky one. So we can calculate the extinction in Gaia's G-band filter for any position on the sky. And then once we have that, we can calculate its apparent magnitude when it reaches Gaia's detector. And then based on its position, we can sample it, the light curve at that position based on Gaia's observation. So you can see Gaia doesn't scan the sky uniformly, but it doesn't matter what position it's at. We can figure out when Gaia observed that field. And that's what this looks like. So these triangles are upper limits, and then our model nova went off, and these red points were detections. So then we have to go from Gaia detecting it to assuming it would be reported as a classical nova, and we would follow it up. So to do that, we're just following the discussion from Simon's paper earlier this year. The main thing is that it has to have detections in both fields of view within 40 days of each other between 12th and 19th magnitude. It also has to be brighter than all the stars within a 1.5 arcsecond radius, and there can't be a 12th magnitude star or brighter within a 10 arcsecond radius. And if we do this, we get a really high recovery rate of about half. And I'm worried that we're missing something in the pipeline here that we're not including in our model. So I wonder if anyone on the Gaia Science Alerts team has any opinions on something else we should be including in here to make this more consistent with the pipeline. So the very last thing we need to do to get a nova rate is just extrapolate from the discovered rate. And you might have seen on the plot I showed earlier that the discovery rate from Gaia has been increasing in recent years. So if we include all novae reported since 2018, we get a discovery rate of around 8.5 novae per year. But if we just do the past 2 years, the discovery rate jumps up to 11.5 per year. And just including this year, the discovery rate is almost 13 per year. So I'm wondering if this is consistent with the pipeline improving, because as you see on the next slide, it definitely matters for the nova rate we're deriving. So what we do is we do a Monte Carlo simulation of our completeness study. We run it 1,000 times each time we get a rate, and then we're gonna plot a histogram and take the median value as the most likely nova rate based on Gaia observations. So I'm showing that for the 3 different timeframes. The 2018 to 2021 gives the lowest rate of only 17, but if we just include this year, it can jump up to as high as 26 per year. So we definitely need to figure out how to be consistent with the pipeline, but you'll see here that none of these rates are 50. None of them are consistent with 50. So we might be deriving a rate that is much lower than previous estimates. So here's my last slide. Our big conclusion is that we're using our galactic nova model, combining that with Gaia observations, and we're getting a nova rate of around 25 per year. And this is much lower than the 2 most previous estimates. So this one right here was done with Gattini discovered, and it's very recent, and we're getting a slightly different answer than they are. So I have a question. Are we overestimating the completeness of Gaia by somehow missing things in the Gaia pipeline? But maybe the nova rate actually is this low because we're doing a similar analysis in Assassin, and we're getting a similar rate, somewhere between 20 and 30. But thanks for listening, and I'll be happy to answer any questions you all have.
Thank you. Really great talk, and it's great to know that Gaia is so good to detect now. But unfortunately, we don't have time for questions. So if there are any, please ask them on Slack. So, okay. So the next speaker, yes, thank you. The next speaker is Jaroslav Merz. So I will wait 10 minutes.
Thank you. Hope everything is there. So thank you. My talk will focus on symbiotic binaries and like the initial phase of the project aimed to search for outbursting symbiotic binaries using the Gaia Science alerts. So first thing first, I will use this one slide to introduce what these objects are for everyone to be at the same level. So these are basically strongly interacting binaries, and interesting is that these are among the widest interacting systems. Usually these are open binaries with orbital periods of hundreds of days, even thousands of days or years in some cases. A typical symbiotic binary consists of a cool giant and a hot compact star, which is mostly white dwarf, but there are some cases where this hot object is a neutron star. And thanks to the stellar winds of both stars, there is a the mass transfer typically from giant to the hot component is via the stellar wind or via Roche slope overflow. And why I decided to work on this project. The first thing is that I'm working on an online database of symbiotic variables. And up to now, there are almost 300 confirmed symbiotics in our galaxy. That's the one thing. Most of them, of course, near the galactic plane and near the galactic bulge. But the reason for that is that most of the surveys is focusing on this part of the sky. But the estimates of the size of the symbiotic population in the Milky Way starts at somewhere at 1,000 something and ends at a few 100,000. So still we are not discovering, or we don't know most of the symbiotics in our galaxy. The second thing is that it seems that Gaia can do that, can discover symbiotics, and there is an example of the project we did last year. It's Gaia 18AEN, which was published in January 2018 as a bright emission line star, which brightened by 1 magnitude. Initially, it was classified as nova, but we confirmed, and thanks to many people which are present here in this room and on Zoom, as the first symbiotic star which was discovered by Gaia. And I will not talk more about this because I had a talk last year, or it was this year, but last workshop, and also there is a paper published. So if anyone is interested, you can read the paper. So the thing is that I would like to know if there are some more symbiotic stars hidden in the Gaia Science Alert. So the first thing which I did is to look for known symbiotic stars which were detected by Gaia among these 18,000 published alerts. Actually, just for a comparison of the number, I put it here that like many of them are classified as supernovae or QSOs or CVs or young stellar objects, but almost 30,000 of them have class unknown. Many of them also are candidates for the before mentioned classes, but there are 12 +1 symbiotic stars. 7 objects actually have class symbiotic star in Gaia Science Alerts archive. 4 of them are classified as unknown, but in the comments you can find that these are symbiotic stars. 3 of them, 1 of them has just LPV in the comments, but it is consistent with a known symbiotic star. Then there is this newly discovered one, and actually there is another object which is coincident with a symbiotic candidate in Large Magellan Cloud, which was detected by Gaia in a fading by 1 magnitude. But it seems that this actually is not a symbiotic star. So in this first phase of the project, we looked for these known symbiotic stars, and we wanted to know how they look like in Gaia data or Gaia light curves, and how these can be distinguished from other objects which are there. Then I will talk about the second phase, which was focused on the objects which Gaia magnitude below 15 magnitude, so brighter, or at the bright end of all of the alerts, and some of them were selected for spectroscopic follow-up. And the phase which is not yet ready or finished is the third one, to search throughout whole archive to select possible symbiotic candidates. So as I mentioned, there are 12 confirmed symbiotic stars which were detected by Gaia. I'm not reading all the names, but what is interesting is these are of like different types, various types, S types which are stellar, but there are also 3 D types, 1 symbiotic star which is in a small Magellan cloud, and also 1 symbiotic recurrent nova was detected by Gaia. Here is where they are located in HR diagram. Like you can compare this with other known symbiotic stars shown by blue dots. The one thing which is needed to mention in connection with this is that, of course, this diagram is distance dependent, and for many symbiotic stars, parallax in Gaia is not well measured, so it's not that easy to identify symbiotics just based on this. And the other thing is that many objects may appear bluer than they actually are, or are bluer, but it makes them not consistent in the HR diagram with red giants. But the reason is that Gaia is also partly detecting not only the giants from the symbiotic system, but also the continuum radiation, as you can see in this figure, and therefore their position in this HR diagram can be inconsistent with a single giants. The other thing we can do is to check the position of these objects in infrared color diagrams, which is often used to identify somehow symbiotic candidates, but it cannot be used as evidence of a symbiotic nature. The reason for that is that there are several types of objects which can share the position. But in this case, you can see where these known symbiotics are located. These 3, for example, are these D types symbiotics, meaning dust, that in infrared there is radiation from the boron dust surrounding the system. And what is much more interesting is how they look like in photometry in Gaia light curves. So always I show here together with the Gaia photometry, which is in red, and the time when the alert was published is that blue, dark blue dot. Also the Assassin or ZTF photometry, if available. So basically in all these cases, which are these 7 cases, the like process which triggered alert was outburst. In these 7 cases, it was so-called classical symbiotic outburst or Z Andromeda type. But also this one last at this figure is the outburst of symbiotic recurrent novae. And what is important to say about this part of symbiotics is that in some cases there is some additional variability in addition to outburst. The fainter objects are not detected in assassin, and the third thing is that symbiotic recurrent novae can be detected only on few data points in outbursts because their outbursts are quite short. But outbursts are not the only thing which can trigger outbursts. In all these cases, the alert was triggered by pulsations or long-term variability, as in this case. So therefore, we need to be careful about what we can expect from potential candidates. That it could not be only outbursts, but also the alert which is triggered by pulsation or orbital variability. And 2 other things which we need to bear in mind is that assassin, if we would like to add some additional photometry, is limited just to brighter objects, and ZTF is limited only to fainter objects, and does not cover a significant part of southern hemisphere. So what we did, we selected the objects which are brighter than 15. It's just a small part, actually, of all Gaia Silence alert, as you can see in this histogram. Actually, 345 objects. We selected only those which were detected in brightenings, not in fading. And we selected the unknown ones, which is 76%. And actually, as you will see, most of them are BE star type outbursts. And actually also in comments, they were classified as BE candidates. Which is the position of all these in HR diagram, and as same figure as was shown before. And the most interesting for us are these dark red ones, which are here. And so these are 8 stars. And the same is the position of these alerts in infrared diagrams. And the 8 stars, which seems to be, and I have to say that this selection was made in this first phase only based on the position in these diagrams to know what other can contaminate the sample. So we ignored the light curves for these 2 slides. So we just used magnitudes and colors. So then we looked for light curves, and actually it seems that from these 8 objects, most of these detections are triggered by pulsation. At least this first one seems to be a like mirror-like pulsation. The 5 other ones are pulsations of with shorter period. And there are 2 objects which have colors and are positioned in the HR diagram consistently with symbiotic binaries, which were detecting longer term brightenings. And this is an important result to know, because as I said, for example, symbiotic recurrent novae can have a similar light curve to the ones shown here, detected in pulsations, because for example, observe only 1 or 2 points in outburst, and it can look like this. For 2 of these objects, we already have spectra, and as we expected from the photometry, when we combine that with what is detected by assassin, is that these are not symbiotic binaries, but just giants detected in pulsation. So basically, to conclude somehow this first stage or first and second stage of the project is that outbursting symbiotic stars might be hidden among the Gaia Science alerts, but we need to be careful that also pulsations or orbital variability of symbiotic stars might trigger alerts too. But distinguishing between symbiotic recurrent novae and pulsations on shorter timescales is difficult when using just Gaia lighters. What can be a hint, but it is not the final evidence, is the amplitude of brightening, because in case of pulsations that will be much less than it in case of outbursts of symbiotic recurrent novae. So the big plus of this approach is that in contrast with majority of surveys, as we heard several times, Gaia samples also the galactic plane. It's an all-sky survey and has a quite broad magnitude range. The small minus is that it has a limited time cadence, and moreover, the filters which are applied to Gaia Science Alert can wipe off likely long period variables, as are mirrors. So some of S-type symbiotics maybe, but definitely this will wipe off most of the D-types from Gaia Science Alerts. So, and that will be the end. Thank you for your attention.
Thank you. We have time for one question. So, yeah, so also, yeah, please, Josh, if you can unmute yourself.
Yeah, do you hear me?
Yes.
Yes.
Okay, I just wanted to mention that I'm observing one of your symbiotics, which is, I forgot the Gaia number, which is SS73141, since about 100 nights in BVI, and I see a clear color change between I and B for this about 100 days. So the data with the AVSO database.
Thank you, thank you. This is actually an interesting object because the Gaia was the first to notice the outburst, and this is the first outburst recorded for the star in the history of observations.
Good. And then just one comment from Siegfried, if you could put the table of discovered symbiotics on Slack or on the chat.
Yeah, sure.
Okay. So if there's any more questions, please write them on Slack. And we go to our last speaker, Zsofia Nagy. If I will show you 2 minutes. Okay. Okay.
All right. So I'm Zsofia Nagy from the Konkoly Observatory in Budapest, and I will tell you about some follow-up observations of Gaia alerted younger active star candidates. And this will be a summary of the work of everyone in our group. So the brightness of pre-main sequence stars can vary on different time scales, from hours to decades, actually, with very different amplitudes from like 0.2 magnitudes up to like 6 magnitudes as well. And the main reasons are accretion, like change in the accretion rate, or change in the circumstellar extinction. For the extinction change, there are like 2 main types. One of them is UX Orionis type stars, which show variations from days to weeks timescales. And these are eclipses due to dust clumps in the disk. And then there is the AA tau class, which show periodic variations on a time scale of a few days. And these are eclipses by an inner disk warp. So this is interesting, but what we are mainly interested in is actually the eruptive young stars class, because this can tell a lot about the physics of young stars in terms of understanding the accretion rates and whether the episodic accretion can be a solution to the luminosity problem. So the luminosity problem is that for young stellar objects, the models have a difficulty to reproduce their luminosities. And one solution which was proposed is the episodic accretion, that from time to time, the accretion rate increases by orders of magnitude, followed by some periods of quiescence and so on. So there are 2 main types of these eruptive young stars. Long-term outbursts are shown by the so-called FUORs, the FU Orionis type stars. And by long-term, I mean decades to centuries. We haven't actually really seen any of these to fade. So there were some candidates, but yeah, that's a long story. So the other type is XORs, which show short-term outbursts. And by short-term, I mean from months to, say, up to a year. And these are reoccurring events that we have observed. And there could be, of course, other types as well, but these are the two main types that we study. So when a star starts brightening, a young star, we still cannot know the time scale, of course. And then what can we do? We can check the spectroscopy, because that can tell a lot about which type it might belong to. So FIORs show an absorption line spectrum, while XORs show an emission line spectrum. Like in this image, there is an example of both. And we still only know about 50 young eruptive stars, which is why it's so important to monitor their brightness of the known ones and try to discover new sources. And these are both important, and in both of these goals, the Gaia Science Alert System is actually really helpful. So when there is a Gaia alert for an interesting young eruptive star candidate, what we can do is, well, first we can check if it belongs to, say, any star-forming region. We can search for archival data, like from the ZTF or PennSTARS or WISE, and compare to the Gaia light curve. Then we have a series from Vizier, where we can check for infrared access, and we have color diagrams as well. These are important tools. However, we still need the follow-up spectroscopy. Well, we do follow-up observations in general, also photometry, with a higher cadence compared to the Gaia light curve. So this list of telescopes is not complete. For photometry, we mostly use 1 meter class telescope in Hungary and another one in Poland, Mount Suhora. And for spectroscopy, we use telescopes from various locations, from the Canary Islands, the NOT, TNG, GTC, and the Liverpool telescope. We use from Chile the New Technology Telescope, and from Arizona the LBT. And though I don't mention it on the slide, but we just obtained some spectroscopy from VLTO. It's coming, I mean, these days actually. So just to give you some numbers about our results, which I will go into details about, we have found in the Gaia Alert system more than 50 eruptive young star candidates, not confirmed, but candidates. And we have follow-up spectroscopy for at least 15 of them. We also have follow-up photometry for even more than 15 of them. There are 2 papers on these Gaia alerts, which are already published. And there's one more which we just submitted a few weeks ago. And we have at least 3 more papers in preparation corresponding to these Gaia alert sources. And now I will show you some examples of the most interesting targets that we work on. So this is the first Gaia alert source, young eruptive star, which our group published, Gaia 18DBY, which was published by Szegedielek in 2020. And it shows a typical light curve, which we expect to see for a FIOR. It was also confirmed, in addition to the Gaia light curve, in WISE, so in infrared, we see the increase of the brightness as well. And the final conclusion was, or confirmation that it is indeed a FIOR, is the spectroscopy, which shows the typical spectral signatures of FIORs, like absorption lines. Then there was another interesting target, Gaia 17AFN, which is V555 Ori. It shows brightness variations, brightness increase on a time scale, which is typical of XORs. However, this is where it comes in the point how important it is to do as many follow-up observations as possible. Because when we looked into other types of data, it turned out that it's actually not the accretion rate that is changing, but the circumstellar extinction, which made this source an AA tau type star. And you can also see the short-term light curve, its test data, and it shows a quasi-periodic variation on a time scale of a few days. And when we plot the magnitude differences, we can see that in the near infrared, these magnitude differences follow the extinction curve. So indeed, we could confirm this is due to extinction and not change in the accretion rate. Then there was another source. I will just mention it really briefly because Eleonora Fiorellino covered it in her talk on Tuesday. So this is a real XOR. So change in the accretion rate. It's Gaia 20EAE. This was just recently submitted by Cruz, Sanz, Demir et al. And so we see an outburst in the Gaia light curve. And when we checked all the archival data, we actually found that a few years ago, around 2013, 2014, there was another outburst with a similar amplitude. And this is another typical signature of XORs, this reoccurring outburst. We also obtained spectra from NOT and GTC, and we compared it to the spectrum of the prototype of XORs, EX loopy, and the two spectra show really similar features, which really gave our final conclusion that this is a real XOR. There are other two interesting targets, Gaia 20BWA and 20FGX, which show, again, brightness variations on a time scale, which is typical of XORs. However, so for these two targets, we obtained follow-up spectroscopy from the TNG and GTC, and we found some tracers of the accretion rate, like bracket gamma and the Balmer lines. So we could obtain estimates for accretion luminosities and accretion rates. So these two figures show how the accretion rates of these sources can be compared to, and luminosities, so luminosities on the left side, accretion rates on the right side, to the stellar luminosities and the stellar masses. All the dots are classical T-Taurus stars, and the triangles are XORs. And our two sources are shown with the asterisks. And as you can see, these two Gaia alert sources are closer to classical T-Taurus stars and not such outliers like for XORs. Well, too bad. However, still these are interesting targets, just not eruptive young stars, but probably variations which are seen in classical T-Taurus stars. And then there was the Gaia alert, which we were really excited about, Gaia 21BTY. Well, we are still excited about it. However, it's doing something interesting. So it was a known young stellar object which increased its brightness with an amplitude which made it suspicious that it could be a furor. So then Lynn Hillenbrand, our collaborator, obtained some spectroscopy with a moderate resolution that you can see there. And she compared those spectra to other confirmed furors, actually two other Gaia alerts, Gaia 18 DVY and 21 and 17 BPI. And these spectra show really large similarities. So there was the conclusion, okay, it's a furor. However, then its brightness dropped. It almost went back to its quiescence brightness. So now we have to explain this. And yeah, so let's hope that for the next Gaia alert meeting, I can tell you some more details about this. Okay, and then we have another interesting target, Gaia 18CJB, which shows a long-term brightening, as you can see in the Gaia light curve. It's not a confirmed young stellar object, but according to Gabor Marton, it's 85% probable that it's a YS, so a young stellar object. So we obtained spectra. I'm not showing it, it's because it's a preliminary reduction, but we obtained spectra using the LBT. And it shows all kinds of accretion tracers like Balmer lines, bracket gamma, and we also see the H2 line in emission, which can trace the presence of an outflow. And we have CO lines in emission. So we have signatures of young stars. However, combined the fact that we see emission lines and the timescale of this brightening, we may be dealing with a peculiar kind of eruptive young stars. So stay tuned for this. Actually, this work is done by Eleonora Fiorellino, who gave the other talk on Tuesday. So, okay, I will summarize what I just said. So Gaia alerts turn out to be a really useful tool, actually, also to identify young eruptive stars, candidates, for which we use follow-up observations like spectroscopy to confirm them as eruptive young stars. And our group already published a few papers on one FUOR, one XOR, and an AA tau type star. And we are writing several other papers, so stay tuned for our results. And let's hope that the Gaia alert system, I mean, I'm sure about it, that it will continue to provide some really interesting new alerts. So that's all.
Okay. Do we have time for questions? So, any questions from the room? Okay.
I just may have a comment. I just looked at the slide, the last one you showed.
Okay.
CJB,
yes.
And it's crazy. And we've alerted in Gaia somewhere halfway through, it's brightening and it kept rising, and then now it's slowing down, and it's like 7 years long life curve of a rising magnitude of 5. That's the range. This is crazy.
Yeah, I agree. It's a really interesting.
And there's no change in Y's you showed. There's no change in magnitude.
Yes, that's curious.
Wow.
Yeah.
I was also wondering this. So this is not typical that we have in obstacle, right? Okay.
This is definitely not a typical source. So we will really need to do a lot more analysis.
Mm-hmm.
Well, unless Y is blended, then you actually don't see it. Right?
It could be, yeah.
That's awesome. So every time we see a microlensing candidate which is then turned down, which is not interesting, then we send it to the Concoli team. They do a lot of good stuff with it. So that's the cooperation.
Okay. Any questions from the room? I don't see them from the Zoom. I have one quick one. In the beginning, when you were showing the spectra of in the introduction, I noticed that some of the lines are symmetric, some are not, and some are double peak. Is this, is there a reason why? Because you would, I assume, all being the same kind of type.
Sometimes we can see some Signy profiles, for FUORs, for instance. It also depends on the spectral resolution, Our spectra were taken at really different spectral resolutions, so we cannot always resolve kinematics in the line. So that's why they are also, they can be different, yeah.
Okay. Any more? So then it's time for the, sorry?
It's time for the group photo.
Oh yes, time for the group photo. So we have the idea, if you could everyone who's on Zoom to turn on the cameras, and we'll take screenshots. And it's the same for people in the room. So
I'm without the mask, but I don't know.
Yeah, I don't know.
Breathe and you hold your breath.
I think one with the mask and one without.
Okay, we'll take one for the officials with the mask.
Wait for the
Okay.
I guess some time to everyone. I think we'll have to do multiple screenshots.
I see everyone in one.
Oh, okay, then perfect.
Right. Maybe I will stop seeing everyone.
I should put my mask on.
Please mute, close your microphone, the audio, because there is a feedback, unfortunately. Are we ready? Wait a second, please. Some problems? No problems? Yeah. Simon, thank you for putting on your mask.
It's just to match everybody else.
Right. Okay, I don't see everyone here, but anyway, I'll be taking screenshots. Right. Okay, 1, 2, 3. And a screenshot. And one more. And we wait. I think I'm taking them, I hope. So now hold your breath and then without the masks. 1, 2, 3. Okay, I think I have it. Thank you very much. And now we can take the real photo outside. For people in here, please, let's meet now in downstairs by the entrance to the building. It's a nice place.
And for the talks, we meet in 20 minutes.
How is it looking? Is it okay? Okay.
Oh. Welcome back, everyone.
Someone has no. Okay, that's fine. No, please.
Okay, welcome back, everyone. So we start the first talk with Sebastian Kurowski. You have 12 minutes and then some for free for questions.
Okay, thank you. Can you hear me well?
Yes.
Perfect. So hello, everyone. I'm a PhD student from Krakow, from the Jagiellonian University. Currently, I'm in Chile at my studentship at ISO. And I would like to tell you about my small project of photometric monitoring of eclipsing dwarf novae using 2 robotic networks of telescopes. So I'm working on cataclysmic variables, especially dwarf novae. And those are systems with binary systems with main sequence star, which is filling its row slope. So there is a mass flow onto the white dwarf, and it's creating accretion disk around the white dwarf in case of non-magnetic systems. This dwarf novae also show repetitive outbursts and super outbursts, and they are considered to be one of the best laboratories to study accretion. And this is because of their short orbital periods and this high variability with outbursts, super outbursts, which let us check how this disk is changing with this variability in a short period of time. The most interesting are high inclination systems because this accretion disk in dwarf novae are very small. So it's impossible to take images even using the largest telescope, take a simple image of accretion disk. It's impossible to resolve them. That's why we need to use some indirect imaging methods. And in case of high inclination systems, we can do this. And there are 2 methods called Doppler tomography and eclipse mapping. The first one based on spectroscopy, on high resolution spectra, taken throughout the whole orbital period of the system. As you can see on this top left panel, here are 5 Balmer lines, hydrogen lines. On the y-axis, you can see the orbital phase. And you can see that these lines are changing throughout the orbital phase. You can see this double structure, but sometimes left part is brighter, sometimes right part is brighter. So this variability is very fast and clearly visible. And this variability is caused by the accretion disk because this emission lines origin from accretion disk, and accretion disk is rotating. So different structures in this accretion disk, like hotspots or spiral structures, rotate and have different radial velocities throughout the orbital period. So in this shape of emission lines is hidden information about the brightness distribution in accretion disk, because every point in wavelength in emission line corresponds to some point in a map of the accretion disk. So using this Doppler tomography methods, from the spectra we can reconstruct the image of the disk. However, it is in velocity space. So in the middle is velocity 0, outside is the highest velocity. So we can say that this image is a bit flipped inside out compared to normal coordinates, spatial coordinates. And usually we leave these maps in velocity space because it's quite difficult to convert them into normal spatial coordinates because we have to assume some velocity field. Having brightness maps in different Balmer lines, for a few Balmer lines, we can also obtain temperature map of the disk. We simply take every point in each of the maps and fit Planck function to our hydrogen lines. And therefore, we got temperature in every point of the map. So even though these disks are super small, we can get not only brightness maps, but also some physical parameters like temperature. And from temperature, assuming some model, we can also derive column density distribution in a disk. Eclipse mapping works in similar way. but we closely look into shape of the eclipse. Eclipse secondary component is eclipsing accretion disk. And of course, shape of the eclipse depends on the brightness distribution in the disk. So again, using high-speed photometry, in this case, we can also reconstruct the brightness image of the disk. Both methods have some limitations, but both should lead to similar results. And also having data in few filters, we can use so-called physical parameter eclipse mapping and also derive some physical parameters of the disk like temperature and column density. Unfortunately, both methods require large telescopes because in case of Doppler tomography, we need high resolution and also high spectral resolution, and also high time resolution. These targets are not very bright, so it's doable usually only with the biggest available telescopes of diameters of 8 meters, 10 meters, and so on. In case of eclipse mapping, we also need large instruments because we need really fast photometry. These systems has very short orbital periods. This eclipse can be few minutes, 10 minutes long, and we really need to cover it very well with observing points. And as you know, getting time on large telescopes is very challenging. And I prepared many proposals for this kind of projects, and it was very difficult to get data because of the unpredictable nature of cataclysmic variables, because of the outbursts and super outbursts. That's why I came into an idea to prepare a photometric monitoring program of the most interesting targets, so bright eclipsing dwarf novae. And the goal was to select targets for future observations and prepare observations using larger telescopes by estimating outbursts and super outburst frequency, and also check the ephemeris of orbital ephemeris to have exact timings of eclipses. I used telescopes located all over the world, mostly based on two networks of telescopes, iTelescope, Skynet, and also telescope located in Krakow. This is one of the telescopes at the Astronomical Observatory of the Jagiellonian University in Krakow. 50-centimeter Cassegrain is semi-remote, so you need a person to set the position of the telescope at the beginning of the night, and then you can control telescope remotely, but you cannot change target to another. So I use this telescope mostly to obtain one light curve of one target throughout the whole night to get exact eclipse timings. The other telescope is a new instrument. It's also a 50-centimeter telescope, but fully robotic. It's a plane wave telescope with direct drive mount, very fast, very precise. And currently it is connected to Skynet robotic telescope network, which I'd like to tell you a little bit more about, because it lets us to control this telescope in super easy way using very user-friendly web interface. Whole Skynet robotic network contains around 20 optical telescopes and also one 20-meter telescope. They're located also all over the world, in Australia, in Europe, in Southern and Northern America. It has automatic scheduling of observations. So we're just giving our target, giving some restrictions, for example, how high above the horizon we can start observing, how far from the moon can be, and so on. But then the system is automatically scheduling our observations in the most effective way. How does it look? We simply give the name of the target, ray ascension, declination, some basic information like maximum sun elevation when we want to observe, minimal target elevation, minimum visible hours, or lunar avoidance. Also, if you have targets like comet or asteroid, you can give orbital elements, which is very, very easy. And after giving the coordinates, we can see the visibility for upcoming 24 hours of our target from different observatories and different telescopes. For example, here's our Krakow telescope. In case of this target, this is Gaia 21 EFS. Then we choose a telescope which we want to use in our campaign. In this case, I'm using only Krakow telescope, as I have the easiest access to this. but also you can include other telescopes from Skynet network. Thanks to this, even in case of a bad weather in Krakow, you can have full coverage of the observations. Then you choose filters, exposure times in each filter, how many repetitions. For example, you can set that you want a set of BEVRI images every 12 hours. So basically every night you have an observing point. You submit it and then you just wait for your data to arrive. It is already reduced for bias and dark and flat field and ready to download, and also with astrometry done. So you have already coordinates, right ascension and declination. iTelescope is totally different. It's based on reservation system. So you need to prepare observing scripts. You need to book telescope for a certain time. It has 4 observatories in Australia, United States, Spain, and in Chile. Telescopes vary from super small refractors to 60-centimeter telescopes. You can check the status of every observatory, but it requires more time, more preparation to submit observations, because you need to know exactly at what time you have to book. You want to book the telescope, then you have to prepare observing script, which is very simple. You just give exposure time, how many exposures, binning, target coordinates, and so on. And then you just wait for your observations to be done. So you have to prepare book telescopes, for example, for 1 week in ahead, because the biggest telescopes, the more interesting one, are usually used a lot by other users. And also, you cannot prepare your observations, for example, for 1 year ahead, because you are limited to 1 reservation per night per telescope. And also, you have limited time of all of your observations. Price of this of every hour or of every minute of observations vary depending on moon phase. So you can get up to 50% discount during the full moon. But it has some disadvantages. For example, at Skynet, calibration images like flat fields, bias darks are taken as often as possible. Here in iTelescope, they take flat fields only when they change some instrument or they see that there is some dust on the image that is not well reduced. So this is a big disadvantage. If you need very precise photometry, this won't work for you. And during the observation, you can check the system status and then just download your data from the server. So I observed around 20 few targets. Data, I downloaded preliminary reduced data for flat field, dark, and bias. I did astrometry of every image using AstrometryNet software, then aperture photometry with source extractor. And for visual check, I also prepared plots of every image because sometimes astrometry failed, so I can check why. Sometimes one of the stars variable comparison or check is not visible because, for example, it's too weak. So I can also diagnose it very quickly with set of JPG files. And let me show you some results. Here's, for example, classical dwarf nova. The points on red are eclipses. These points are used to create preliminary O-C diagram. These errors are big because they correspond to the length of eclipse. And also on the rest of the points, I use PDM analysis, phase dispersion minimization, to check the period of the system, outburst period, and it's around 46 days in case of this system. And I did similar analysis to other targets. This one is very interesting. This is exactly the same analysis. The PDM analysis resulted in a period of 26 days. And this is very interesting because in previous work from 2008, they also checked this variability of period of outbursts in time. And they seen that my period is around 26 days, so it's around here. But after some time, there was a significant drop to around 12, 10 days. So it looks like the system is back to this normal stage of longer period of outburst. And many, many more light curves. also long-term light curves and eclipses from 50 centimeter Cassegrain, which will be used to obtain O-C diagrams. And at the very end, I just want to mention this last target, ASAS 14AG, because this is a very interesting target for which I applied for Gemini and SALT in TAO mode, and I got time for fast photometry at Gemini and high resolution spectroscopy at SALT. These observations will be taken close in time and will be triggered after the system declines from outburst, so to catch it in quiescence. And to trigger these observations, I need to further monitor this target. It needs like one or few points per night. That's why I wanted to ask for help, because we have this big community of observers here. This target is quite bright. It varies up to, let's say, 17th magnitude, the lowest. And this observation will be needed most importantly in January. And based on them, I want to trigger these observations to make them almost simultaneously, and therefore to combine these two methods that I told you before, Doppler tomography and eclipse mapping, to get rid of limitations of both methods and obtain the most complete image of a accretion disk in this system. Thank you very much for your attention, and sorry that I took a bit too long.
Thank you for the talk. Please, for any questions, could you write them on Slack, because we're slightly over the time. So yes, I'm sure there will be. Okay, so our next speaker is Josh Hamsch. If you could please share the screen, Josh.
Hello, do you hear me?
Yes.
Can you see my
and also
slides?
Yes, can you try sharing in the full screen?
Yeah, I'm just trying, yes. Okay. Can you see the full screen?
No, it's still the same as before. I think you have to.
How can I switch to full screen? I mean,
you have to stop sharing and you have to start sharing again, not the window PowerPoint, but the entire desktop.
Yes.
Okay.
Can you start again, but just the whole desktop? Try it again. And try the presentation mode.
Okay.
Okay. Yes.
It's okay now? Okay.
Yes.
So yeah, thank you to Lukasz for giving me the possibility to show follow-up of Gaia alerts, Gaia 20 FNR and Gaia 21 CCU from the remote observatory Atacama Desert. I mean, this observatory was already mentioned in the previous days, and I'm now showing you what are the possibilities of those of this observatory. So I'm actually a retired nuclear physicist and yeah, maybe a professional amateur astronomer. I'm a member of different organizations. Of course, I live in Belgium, the Flemish amateur organization, the American organization of variable star observers, the German one, because I'm German actually, and the French one, GEOS, which is more for RLIRA observations and has the RLIRA Maxima database. So Rod is actually at San Pedro de Atacama at the space ops facility of Alain Maury, which is a Frenchman who worked at ESO in the past and has changed his direction towards showing the visitors and tourists the night sky in the Atacama Desert. So before the pandemic, at least, it was very touristic with restaurants, hotels, internet, power, and water. It's about at 2,500 meter elevation, and it has an exceptional number of clear nights. I'm there now for 10 years, and among these 10 years, I observe between 312 and 345 nights a year. The equipment I use at Rode is off the shelf, so it's a 40 centimeter f6.8 optimized dial Kirkham scope from Orion Optics in the UK. It's sitting on an ASA Astrosystem Austria direct drive mount, which is very fast. It was already mentioned by the previous speaker on a different direct drive mount. It uses an FLI ML16803 CCD with UBVRI Astrodon photometric filters. I use standard software for data acquisition. I mean, image acquisition, I use MaximDL. For the automatization, I use CCD Commander, which is a very, very easy to use software for changing targets. You just add 2 lines and that move to the target, and then the number of observations, and that's it. And LESFA Photometry, which is a photometry program which is developed by a Belgian amateur astronomer, which I met in 2009, actually in the US. And VNC for remote access to the local PC. The nightly observations are made in a special way. I mean, I observe 30 to 50 target stars. So of course, many stars outside of the Gaia alert system, depending on the season and requests. Normally I do snapshots in BVRI or BVI filters. I do 2 images per filter, just to be sure that there is at least one good photometry. And then I do time series in sequence with between several targets, 3 to 5 stars, and every few minutes cadence. So because of the mount is very fast, it can move from one target to the next very quickly. And of course, if there are special requests on targets which should be observed solely during several hours, that this can also be accomplished. I am observing since I don't remember 100 nights BVI images of VV high-tree CV during outbursts and at quiescence for somebody who is interested in this data. This is an aerial view of space ops. I mean, can you see my cursor? I mean, here you have the remote installations of telescopes. So this is my telescope here, the red point. And this is the house of Alain Maury. And actually, these are the different telescopes he uses, and they are on plain air, because as you see, there is no real vegetation. So it's a really dusty area for the tourists to come every night by buses from the town to show them the night sky. And here are some lodges where you can stay for if you visit your observatory or just for visiting. So this is the observatory. It's in a clamshell dome, so it can observe the whole sky simultaneously. That's why I actually can move from one star to the next in a series without the dome need to follow, because that would have weared out every possible moving part on the dome already. I have a film. I'm not sure if it can work via the connection, which shows the night observation of the telescope during one night. So it goes from from one object to the next and goes back. And yeah, and you see, of course, the night sky, the beautiful Milky Way in the background, and you see the scope moving, and probably you cannot see all the movements it's really doing. And yeah, this is has been done by the landlord LMRB a couple of years ago. Okay, now I go back to my presentation. Can you see the presentation again? I hope so. So the very first Gaia Alert microlensing event was 19 BLD, where I was mentioned in the ATEL 12.9.4.8, and the paper has been submitted by Chris Robicki, and I have marked the amateurs, at least from the list of affiliations which have contributed to these observations. And then Gaia 20 FNR follow up. So I observed it in 3 filters, BVI, for about 310 nights. Of course, there was the gap of the star being too close to the sun. And then I immediately tried to observe it even at the high air mass after it came back. And it was really at the right time, because then the maximum, at least in the V band, was observed more or less in full-blown way. This is a model from Chris Robicki. He showed already this in his presentation. It's rather important to get this kink here in the light curve, and of course to continue the light curve till it goes back to the pre-lensing mode. Gaia CCU 21 CCU, it's an alert from this year. I observed it during 160 night. Of course, there was also a gap of close solar conjunction, and I observed it in 3 filters, BVI again. And you see this 2 cusp behavior of the light curve, which was already shown by a previous alert from 2016. And let's see how it continues in the near future. So of course, these are not all interesting targets which I have observed in the past 10 years from road. I mean, the most prominent one to me was RSCO, the first white dwarf pulsar, which was a Nature paper in 2016. So my first Nature paper, even though I'm a professional nuclear physicist in nuclear physics, Nature papers are very rare. We have found a new candidate, white dwarf pulsar. Actually, Taichi Kato from BSNet has been found, and I observed it, and we have a paper on this also. And then there is a very interesting system, J1407. It's a ring system, a huge ring system. It has dropped in brightness by orders of magnitude over nearly 2 months period in 2007. And since 2012, I'm observing it. Unfortunately, we have not really been able to find a new drop. And other observations, intensive Norway, cataclysmic variables, luminous blue variables, Lyra stars, and symbiotic stars. So I actually can observe the star which was mentioned just in the previous presentation, Assassin 14 AG, probably from my observatory. And Most of the papers, in the meantime, they are 110 and counting with co-autorships can be found on archive, searching for my last name, Hamsch. There's only one with this name. And in conclusion, so variable stars observations open lots of possibilities for an amateur to contribute to scientific research, and participation in alerts and requests for observations like AVSO, Assassin, Gaia alerts, individual researchers request give the possibility to contribute to scientific research. And yeah, in the meantime, I had collaboration with many professional astronomers, as mentioned before, more than 110 referred papers on archive. So thank you very much for your attention. This is my email address, and I would like to rejuvenate, please rejuvenate the email list for priority targets, because I mean, I'm not generally looking at BH Tom, Black Hole Tom, what is really of interest, and you could send even only once a month a priority list for targets, especially in the Southern Hemisphere. Thank you.
Thank you, Judge. Yeah, it's really interesting talk and amazing. I know that you're producing great data, and I must say, really beautiful movie that you showed. Thank you. Do we have any questions? In the room? Łukasz?
If I can just comment on the mailing list, of course we can do that, and I just have to think of ways of combining the two. So maybe we will introduce some kind of subscription service, Black Hole Tom emailing the most interesting events automatically, and to send emails like a request, because we don't want to miss your data not being taken for our events. This is so great.
Thank you.
So that's a good idea.
Thank you.
Any questions? Like I said, it's really beautiful data that you're getting. So thank you for that. For additional questions, please write them on Slack or on the Zoom, preferably on Slack, so that it doesn't disappear. So our next speaker, we move to Alexandra Grukajska. I'm sorry, Grukajska, yes. If you could share. Okay, and I will show you for 2 minutes.
Oh, okay, thank you. Hello, dear colleagues. I'm happy to present my talk offline, and I want to say thank you for organizers to let me this opportunity. My talk will be about 1 meter Smith telescope in the main, but I briefly touch some other devices from our laboratory. So I work in Special Astrophysical Observatory. I am the junior researcher. It is located in the North Caucasus. It's here and here. We have two scientific platforms. It's an upper scientific platform where is located our telescopes, for example, 6-meter telescopes, and lower scientific platform where we live. Also, I represent my laboratory of spectroscopy and photometry of extragalactic objects. These photos, this is not all of us, but this all of observers in our laboratory. We support more than 70% of observation on 6-meter telescope, and also we are in supporting team, ground-based supported team of Spectre RG space telescope. But now I will talk about smaller telescope. It's a Schmidt telescopes. These telescopes have excellent optics and mechanics, but they have outdated control systems, and so the technical progress make it possible to rework some control system of these telescopes. We are interested about this system because they have some strong points of observation. For example, large field of view, high transmittance, low level of scattered light, high focal ratio, and they are good for detecting low surface brightening levels, surface photometry of galaxies, and photometry of stars. In 2013-2015 years, we upgraded 1 meter Schmidt telescope. It's a famous telescope of Burakan Astrophysical Observatory because the first and second Burakan surveys were made in this with this telescope and give us Mercurian galaxies. Schmidt Burakan Astrophysical Observatory, it's a top 5 of Schmidt system telescope by mirror size. And nice with observation is this observatory quite better than amount of night of observation in our observatory is 65%. In this telescope, we use some amateur camera, but we reworked this camera and we vacuumed volume with the CCD detector and replace cooling with air by cooling with liquid. So now our working temperature for this detector is -40 degrees. And also we acquired this camera with some set of filters. It's 20 medium band filters, 5 broad band filters of SDSS system, and 3 narrow band filters. And we located these filters in 6 wheels, so we can change it very quickly. This is how our detector looks like. This is a telescope, and this is screenshot of our control system. So we can control filters, we can control exposition, we can control number of exposition, we can focus in telescope from here and create some log after the observation. Now I want to show you some brief results. This is photometry of galaxies, and we can receive a very low bright surface. For example, for G band, it's a 28 magnitude from square second. These galaxies were observed for program of dark matter within the optical radius. Our colleagues from Armenia observe and make some science with young stellar objects. It's a paper of this year by Mosisyan. They found 20 new Herbig-Haroch knots and 20 new objects. Also, we can observe very low bright surface for ionized clouds. It's a Mercurian 1 galaxy with active galaxy nucleus, and this is a ionized cone from Aegean in the center of galaxy, so we can see it. It's a great deal because I made some PhD thesis with this. We observed 2.5 field, square degree from field. It's very big field, it's a moon in our field. And after that, we can make some spectral energy distribution with subtractor. And in this picture, you can see the SDSS spectra for galaxies and our spectral energy distribution. As you can see, we can clearly see some spectral features, for example, H alpha, for example, Magni. and so on. This picture shows some distribution for our samples. It's distribution in R filters, in redshift, and so on. And one linked work with this spectral energy distribution is work with the quasars in this field. We can make some spectral energy distribution for quasars in this field, and we found some quasars, some distant quasars at redshift 4 or more. And after we can construct this distribution, we can check it on the 6-meter telescope, and we check it. So we get some spectra. You can see it's here. So we go to the 6-meter telescope. On the 6-meter telescope, we have 2 devices, Scorpio 1 and Scorpio 2. We have some mode of each devices. It's a direct imaging, long slit spectroscopy, and for Scorpio 1, it's a spectropolarimetry and interferometer of Fabry-Perot. You can see example of these images here. This is telescope. This place which is located in Scorpio. Is Scorpio. And I want to show some specters from Scorpio 1 or Scorpio 2. I can't remember which devices did. It's our galaxies. It's something about 0.3 redshift. So it's in our filter we have a 20.6 magnitude, so we can see clearly all the spectral features, and this spectral was obtained by exposure 1 hour. For more brightness, bright objects, for example, nova in M31 galaxy, it's something about 17 magnitude in V filter. We have this spectral, it's only half of hour, so we can do this with this device. And also, we have one more devices for the 1 meter size telescope. It's a great deal by Viktor Afanasyev. It's his last device. Also, it's a small brother of Scorpio and Scorpio 2 devices, and you can listen more in detail, of course, tomorrow by Elena Shablavinskaya. But I want to show the spectra from this device. It's Sacred 1 galaxies. It's a 14 magnitude and 1 hour of exposition, and the spectrum looks like this. So that's all. This wonderful picture from our Schmidt telescope. Yeah. That's all.
Thank you. We have time for questions. I must say it's really impressive and great data, it looks like, especially to do spectroscopy on 21 magnitude objects. So do we have any questions in the room?
So we are doing these STDs for galaxies, and with this large field of view, are you also extracting STDs for stars? With so many in the field of view?
We extracted all objects of this field of view. It's something about 100,000 objects, but we limited our sample by threshold magnitude in our filter. It is 22.5. So we have only 17,000 galaxies in this sample. And we remove stars by Gaia, by legacy survey. And,
you subtract them?
Yeah.
Okay, but having so many filters, let's say, middle filters or narrow filters, you can really well establish SVs for particular star which may not have spectroscopy available. So it provides a great sample for people who study variable stars. So you can say that.
Yeah, it's great, but we do studies with extra-galaxy objects. But if somebody wants to make some collaboration about stars, of course we are open to this.
Okay, thank you.
Pavel?
Yeah, very nice presentation. As we discussed already, it would be really nice to have you and your telescopes implemented in black hole dome and to see your data and to process your data. The immediate one, only from 1 meter telescope, but also in terms of spectroscopic classification of our fainter sample of microlensing events. It would be really nice to have some spectra from the 6 meter Russian telescope. So for sure we should stay in contact.
Of course.
Any more questions? Sorry? Yeah, for additional questions, please write also in slides. I was just wondering, the field of view for the 1 meter telescope, what was it? It's really big.
Whole field of view is 16 square degrees, but we have only one detector, so our field of view is 1 square degree.
Okay, I mean, still impressive. Okay, great. Okay, if there's no more questions, our next speaker is Agnieszka Słowikowska, so please you can share, and I will show you the 2-minute warning.
I cannot turn on my camera.
Okay, it's okay.
Because I'm not moderator.
Oh, way. Oh, I thought that
Can you say?
Sure.
Okay.
Okay. Welcome everyone. I'm Aga Słowikowska from Nicolaus Copernicus University, and I'm Vice Director of the Institute of Astronomy, and I'm responsible for the infrastructure. So today, briefly, I'm going to talk about the facilities that we have at our observatory. Unfortunately, we don't have the 6 meters, so I really feel bad. Change it. Yeah. So Toruń is west north from Warsaw, and the observatory is 10 kilometers from Toruń. And this is the picture of Toruń, and as you might know, probably, Nicolaus Copernicus was born there. Therefore, of course, our university is of his name. This is the view of the observatory. We have 2 radio dishes. One is the 32-meter dish, the other is the 15-meter dish. And here are the optical domes. So in the first dome is the biggest optical telescope in Poland with the 90-centimeter mirror. Then in the second dome there are 2 smaller telescopes. In the third dome we have the historical Draper telescope, and in the fourth dome we have the 60-centimeter telescope. So this is R42, and it's 32-meter dish, and it's we have following receivers on the passbands C1, C2, L, K, and X, which probably doesn't tell you more much to the optical people, but you have the frequencies given in the brackets. So it can operate in as one of the antenna of the VLBI, so European VLBI network, or as a single dish. And the VLBI sessions takes like 16 weeks per year. So the other weeks are basically for either a single dish mode or a subset of smaller subsets of EVN dishes. So yes, last year, while the telescope was already more than 25 years old, we have We had to paint it to protect it from the corrosion, and it was pretty challenging. So as you can see, so last year we finished all that work, and now we are already in operation. This is very recent fast radio burst spectrum. So on the x-axis you have time, and just please note that the burst lasts only 10 milliseconds. Here you have from 10 to 110 milliseconds, and on the y-axis is the frequency, and of course this is the L-band. Going to the optical telescope, we also have the Schmidt-Cassegrain telescope, which can operate in the mode of Cassegrain with the aperture with a mirror of 90 centimeters, and we have this Copernicus-Cassegrain spectrograph there. Of course, this is low-resolution spectrograph, and more details are given on the slide. And in the Schmidt configuration, we can use it either for wide field photometry or spectroscopy, and here are the details of the cameras. For the up to now we were using SBIC, but now we have a new CMOS camera from the Moravian Instruments, which is C4, and it will be 4K by 4K, so the field of view will be 72 by 72. And we have a new filter with the big square filters, the 50 by 50, and we have the UV-DRI and slow and H-alpha. So, but what is of course the greatest advantage of the Schmidt, that is we can also use this objective prism. So we have the blue and the red, and therefore you can make a spectra of white field of view of the stars. And here's an example. This is the open cluster Trampler tree published by Maciejewski and Bukowiecki in 2010. So on the left is the field of view. In the middle, you can see already the spectra from the objective prism of 12 stars, which are brighter than 12 magnitudes. And as you can see, the resolution is between 5 angstrom on H-alpha and 20 angstrom around the H-beta. So, and after 17 years of not doing that, we're recoating our mirrors with aluminum, and this picture was taken just a week ago, so it was already assembled on the telescope. And on the right, on the left picture, but on the right, you can see Pavel, who is going to join our team from the 1st of January because he got a postdoc from the ORP project. We can do, so with the Schmidt-Cassegrain, we can do both. We can do photometric spectroscopy, but also now we can do polarimetry. We are using for that 2 Savart plates, which are oriented by 0 or 45 degrees, and you can see it on the images. So each star is projected as 2 images, and from that you can calculate the Stokes parameters, and of course here we measure only the linear polarization. And there are some previous results, but they are still before aluminization and with old cameras, so I hope we can improve that. These are the example images. So as you can see, these are the Savarts oriented by 0 or by 45, and having the Savarts already and the objective prism, I hope that we can start to do low resolution spectropolarimetry. I think it will be challenging due to the fact of many targets in the field of view. If it's too crowded, it might be a problem. But if it's not that crowded, I hope we can really do it. And within a year time, maybe we should be able to show you some results next year. So this is our idea. In the second dome, we have the most modern mount in our observatory, which is GM4000. This is from 10 micron, Italian company. And on that, for the moment, it's just a 20 centimeter telescope, but there will be the other one with the mid-35. And for that, there's 2 telescopes where on the bigger one, we will have so-called TNPO, which stands for Toron and Polarizer Polarimeter. Here, the idea is a bit different, because what you have is non-rotating Savarт plane and rotating half-wave plane. but you can also do it in the configuration when you put the quarter wave plane, and then you can in principle also measure the circular polarization. So here we will be able to provide simultaneous photometric and polarimetric observations with this telescope that is in the second dome. And then in the third, we have this historical telescope, and this is the last dome, which is 60 centimeter Cassini. And there we have FLI camera there. It's 4K by 4K, and usually it is used for exotransient studies, the telescope. And we also, of course, luminize the mirrors there, and you can see here, there is also power here. So he was helping us a lot.
In the same time.
Yeah. So, but we also recently were able to collaborate on ISA project, and this is the NEOPOL, which is the Polish polarimeter for near-Earth objects. And the idea is to measure the polarization as a function of the phase angle, and from that we can learn a lot about the composition of the asteroids. So this is within our department. We also have Institute of Physics, where a colleague of ours, Piotr Kolenderski, he has a single photon application laboratory, which is absolutely great and useful because we can go there and test our optics. And here is the lab test of the NEOPOL. And we can also use this laboratory for us for some other projects. So this is the 60 centimeter telescope with the NEOPOL, and of course the problem with double Wollaston polarimeters is the field of view. So you really need a finder to be able to locate yourself, especially that, I mean, this old type size telescopes, you point manually, right? So you have to be really sure where you are on the sky, and this to, no, it changed. So here you have the comparison of the field of view for the finder on the left-hand side, and on the right you have the field of view from, from the Wollaston prism, right? And notice the very small field of view, which might be a problem if you go to the case when you can see only one star, then the astrometry is generally impossible to do. And of course, you have to be very careful while treating the flat fields, because the evening and morning skies are very highly polarized. Therefore, of course, you will see different intensity in each of the respective slits. We also have ALP station, which this is the project that the guys from Wrocław are conducting, and the PI is Sylwek Kołomański, but Przemek Mikołajczyk is also involved in that. So if you want to talk about ALPS, Przemek is here. It's really cool system. So basically, of course, we have the all-sky camera. Also, we measure the SQM, and here on the here is the map of Poland, where the greens it shows already the stations that are already active, and the red are in progress, and gray are planned, or something like this. Ask Przemek, but anyway, I mean, our station is working for more than a year time, which is fantastic, because from that measurement we can say, I mean, how many nights, dark nights we have, and this is basically the histogram, where on the x-axis you have the night sky brightness in magnitudes per arc second, and on the y-axis is the fraction of the time beams, right? Something. So we can go. We are not that bad. Let's say that we have like 50 nights per year. Of course, I mean 10 kilometers far from the city, and on the, let's say, 80 meters level above the sea is not the best location, but we are not doing that bad. So to summarize, here we have then 3 optical telescopes, or let's put it this way, 3 domes where we have the optical telescopes, where we have also 1 radio telescope that is in operation, and we can perform photometry, spectroscopy, and polarimetry. Also, this is, I hope, next year, spectropolarimetry. And for the moment, we're developing 2 projects, this TN4 to build this small polarimeter with rotating halfway plate and non-rotating subarc. But we are also working on the instruments which will give very high time accuracy. So it's based on the single photon avalanche diodes, which is kind of similar to Optima, as Vasilis was mentioned in his talk. And on the right-hand side, you have this is the Skinakis telescope with the Optima mounted on it. And this is the first candidate of the optical magnetar. And you can see that the red color indicates the integration time for the CCD camera, and just below you have the two flares of the magnetar taken with the Optima, where the time is when you can record single photon with the accuracy of a few nanoseconds. So, depending, of course, on your source and on binning you want to choose, you can go to very high time resolution. So from here to here, this is like 100 seconds, and from here to here, it's just 40 seconds. So we are developing kind of similar instrument. And in principle, Japanese, they have already shown that with the 35 centimeter telescope and with APDs, you can get the optical crab light curve, which is 16.6 magnitudes. Within 7 minutes, you can already get the light curve of the crab, which is rotating 30 times per second. So it's really will open some new niche in this photometric business. And regarding multi-wavelength approach, you can, for the polarization, I recommend the book that was just published in Springer. And it was our, we collaborate on it with Roberto Mignani, Andy Shearer, and Silvia Zanna. When there was a European Week of Astronomy in 2018, we had a special session for the multi-wavelength polarimetry, and this is the result of the session. Thank you very much. I hope I didn't overdo it, right?
No. Time for one short question.
One short question, one short answer. What's the limiting magnitude you expect for this extreme time domain?
Depending on the telescope, because I assume that it will be similar as Optima Gas or IQI, which are the biggest European project in this business. They are movable. So we can always, have the gum and...
But here at Skinakis, for example, what's the limiting magnitude?
So we were there on the, at least, 20 magnitude. This is when you go to the light curve. It was below 19, yes? With 1 second resolution.
19 in 1 second. Wow, that's impressive. Okay, and then with nanoseconds, it's of course.
Yeah, of course. Then it's you need to have brighter, but especially for the pulsars, of course, because you add the signal modulo period. So then, of course, you accumulate more.
Cool. Thank you.
I have one short question. So you said for 17 years you haven't done coating. How did you do any cleaning in between?
Yeah, cleaning, yes. Yeah, it's really embarrassing. But for some, there was a huge, there was a big group of people working on the spectroscopy, but then unfortunately our colleagues either got retired or, they passed away. So somehow it shrank, and then, not many people were using really the Schmidt telescope. So we are now kind of trying to get this to the business. So of course, this Gaia alert would be really great to join.
Okay, thank you. Yeah, for any additional questions, please write them on Slack. Okay. Can you stop sharing? Okay. Okay. Yes. Good. Now our next speaker is Sebastian Kaufmann. I hope that I pronounced him incorrectly. I'm sorry. So yeah, I will show you the 2-minute warning.
Okay, I'm going to talk about, no, don't unmute. Okay. I'm going to talk about time domain astronomy in the context of relativistic jets. And for those not familiar with blazars, those are relativistic jets which are launched from supermassive black holes, and the jet points towards Earth, which means the emission from those relativistic jets is Doppler boosted, and time scales of variability are shortened. So those jets emit throughout the entire spectrum. So from a physical point of view, they are very interesting because those are the most extreme persistent particle accelerators in the universe. From a purely astronomical point of view, they're fascinating because you can apply all the astronomy techniques throughout the spectrum. And here I'm showing light curves covering the whole range from radio to gamma rays of one of the best studied blazars, 3C279. And they're strongly variable with timescales from minutes in gamma rays to years and decades in radio. So clearly those are targets for time domain astronomy, and those are targets inherently important for multi-frequency observations. So I want to briefly give an overview of two monitoring programs out of many that focus on blazars. One being the optical polarization monitoring with the RoboPol instrument here at Skinnekes Observatory, which those who are locally here had the chance to visit yesterday. And I think Vasilis probably already talked a bit about RoboPol on Tuesday. Unfortunately, I wasn't able to listen to that talk because I was actually on the way down from the observatory after staying there for a week. So in the context of blazars, optical polarization is interesting because both the angle as well as the fractional polarization is strongly variable. Typically, the angle varies quite erratically and is often described as a random walk, but occasionally we find events where the angle changes consistently in one direction over a longer time period. And interestingly, some instances have been found where such swings of the polarization angle happen exactly at times of strong outbursts throughout the spectrum, in particular at gamma rays. So if those two types of events are really connected, the optical polarization, which tells us something about the magnetic field in the jet, could help us better understand gamma ray emission from those sources, which isn't clearly understood yet. So with RoboPol, we were asking the question if those two types of events, gamma ray flares and optical polarization angle swings, are physically linked. And for that, we observed a sample of about 80 sources for 4 seasons and published a series of papers on that subject. And the only thing I want to point out here is that our main finding was that those two types of events are actually linked. The occurrence of swings and flares at the same time couldn't be explained by pure random coincidence. Now, when we study optical polarization angles, in particular the changes of polarization angles, we have a problem. Because if you have two measurements, for instance, like this, and you want to measure the change between it, it could be 90 degrees, could be 90 degrees in the opposite direction, could be 270 degrees in either direction. So if you make a measurement, you never are sure how fast the angle actually rotated, because we have this 180 degrees ambiguity. So in a recent publication, we studied how fast can those angles actually change, and we found that to make those measurements more reliable, we would actually need daily observations or even better intraday observations. And as much as I would like to see a new RoboPol program with multiple telescopes involved, of course, it was hard enough to get one telescope dedicated to such a program for 4 years. Getting multiple telescopes involved is even more costly. So of course, an alternative approach would be to follow up on alerts. So from that perspective, I think it's quite interesting that a program like Gaia now is able to trigger longer timescale events like flares. With RoboPol, the main program has stopped years ago, but we still use RoboPol, and we observe quite a range of targets, X-ray binaries, white dwarfs. Alex is leading that program. This year, we observed some supernovae. We followed up on a few tidal disruption events, and I think tomorrow Yanis Liodakis will give a talk about that. And of course, we still continue to observe AGN, quite often triggered by gravitational wave, GeV, or neutrino detections. So now we move to a completely different frequency range. On Monday, we've already seen a few nice images from the Mojave project, which for years continues to produce series of images of radio jets. And another big program is that of the 40-meter telescope at the Owens Valley Radio Observatory. So this is a single dish project where we produce light curves. And with this telescope, since 2007, we're monitoring more than 1,800 sources, mostly blazars, but also some narrow-line CFAT1s, brightest cluster galaxies, a few X-ray binaries, and occasionally we follow up on transients. We observe those sources 1 to 2 times per week. So I want to briefly show some of the latest science results that came out of this program. So this is a particularly interesting source. So typically we see flares in those blazars, which can be explained by an exponential rise and decay. But in this case, we found 4 of those U-shaped events, which are highlighted by the reddish background. And those are highly symmetric, which you can best see in this case here. They're not only symmetric, but achromatic. Here I'm just showing the 15 gigahertz light curve, but we have other frequencies available as well. And well, we've already heard a lot about microlensing yesterday. So basically we have the same physics here, only in this case, we have a jet which is moving behind a binary lens that's potentially located in a foreground galaxy. And in the recent publication which is submitted, we show that actually all those 4 events throughout all the different frequencies that we have can consistently be explained with one single model. And quite interestingly, the mass is in the intermediate mass range, so 100 to 10,000 solar masses, which of course is an interesting result. Another amazing source is this one, and here we are really lucky with having monitoring programs observing this target for many, many years. So combining haystack data, Michigan data, and in blue our own data. From the 40-meter, we cover 46 years of observations. And you can see something that looks like an oscillation here in the first part of the data. Then it goes away for about 20 years, and then comes back. It looks amazingly sinusoidal. And you can fit both parts individually and find that the period and the phase align really neatly. So we went into a thorough statistical analysis and could show that the typical flaring activity of blazars, which can be described by red noise process, is highly unlikely to produce this oscillation pattern. So this is a more than 4.6 sigma detection of an oscillation. And we think that this makes this the best candidate for supermassive black hole binary source. Which of course is interesting in context of gravitational waves, because at this mass range, this might be detectable with pulsar timing arrays. So this is clearly a target to follow up in the context of multi-messenger astronomy. And continuing in multi-messenger astronomy, we were also interested in the question of the origin of neutrinos and wanted to find out if we can find blazars in our sample co-spatially with the error ellipse of neutrino events, which showed strong flaring events at the time of the neutrino arrival. And indeed, we found that a quarter of those neutrino events had strongly flaring radio sources co-spatially. There's no consistent picture yet, so we've found cases like down here where the neutrino arrives exactly during strong flaring period. We found cases where the neutrino arrives during the decay of a flare or during the beginning of a flare. But still, it's suggestive, and we tested if those could be just happening by random chance, and showed at a 2 sigma level, this is not the case. So it's not a strong support for the hypothesis that radio flaring events and neutrinos are physically linked. But it's something that clearly shows we should follow up on this. And as I said, just a quarter of the neutrino events actually had flares. So one explanation could be that our sample might actually be biased against most likely counterparts. So the way we want to follow up on this is we drastically want to increase our sample to 5,500 sources, which combines different complete statistical samples. And we will be able to to observe them every 12 days. And well, whether there are synergies between our monitoring program and other programs like Gaia or ZTF, that's something I would like to leave up for discussion. And before I stop, I want to leave with this image which I took 2 days ago at Skinnekes Observatory in the morning. Thank you.
Thank you, really great talk. I have a few questions, but we will ask all of them later. But just one regarding the intermediate mass black hole that you mentioned, that is a possible lens. Were you able to determine the distance? How far is it? And do you know, is it, I mean, did you try to check the optical, if it's a single, if it's in a galaxy or?
So this is a very complicated system. We have the blazer, which is the Luck type. So the blazer itself doesn't have spectral lines, so we don't know its distance.
Oh.
There is a galaxy which is aligning with it. And we had a lot of discussion back and forth, and one of our papers is entirely focused on that, whether the Luck is sitting in the galaxy or if it's just an alignment. And we think it's just an alignment. Because it's a spiral galaxies, and BLUX don't sit in spiral galaxies. So the galaxy distance is known, and it would make sense if the binary lens is located in the galaxy, but we don't know for sure.
Okay.
Just to follow on this is fascinating, and I've been following strong lensing as well in radio for many years. But here, isn't it the case that you have the gravitational lens, which is the galaxy, and it's just a composition of stars. So instead of just binary systems, you have a multiple lens system, and they create this system of complicated caustics. And then the shapes you see are the source, your laser actually crossing those caustics, isn't it that case?
Well, we use the binary hypothesis because that is the easiest model to our knowledge that can produce a symmetric event with those two spikes. So, and then of course we have the typical blazer variability on top of that. So we have that in between. And so it's not just the binary, but there is a larger mass distribution on top of that so that you can actually get the shape. So there are three components to the lens model that is applied in the modeling of these events.
This is fascinating. And do you have also the optical library for that one?
I think it doesn't go into the modeling, but it's discussed in one of the papers. And I have to say, I don't remember if it's showing similar patterns. I don't think it is.
But I see a perfect pilot case for our ORP grant here. Long-term multi-wavelength radio optical observations of such systems. And
we have 2 or 3 more targets where we've seen similar shapes, but just one time. This is the only one which seems to do it recurrently. And interestingly, it seems to be happening at similar time intervals. So our prediction actually is that we will have the next event sometime next year, which would be very nice.
Excellent. We want to talk to you more about this later.
Any quick questions? Or okay.
Just a quick question. The radio monitoring that you do, the cadence is 12 days, you said, right?
Currently it's 7. So with the current sample of 1,800 sources, it's 7. Once we go to the 5,500, it will be 12 days.
I was just curious. I mean, wouldn't it be worthwhile to have to sample it in non-regular intervals? Since you have such a big sample, the timing not to be always the same. I don't know, would it make a difference or in identifying some different periodicity, that's all.
Well, the way we're creating the schedules gives us roughly the same time intervals. So we update schedules every cycle of observations. So on average, we have weekly sampling. We have never considered observing some targets with different time sampling as others. One point being that the original point behind the program was correlation analysis, and once you change time sampling, it gets even more complicated than it is in the first place. It would also make our the creation of schedules much more complicated. And you never know what those objects are doing, because we have targets which are not doing anything for 10 years and then go off the rockets. So the more conservative approach, I think, is keep it all in the same way and comparable, especially if you want to go into statistical studies, because those get more complicated when you have changing cadence.
Like I said, for any additional questions, please ask on Slack. And yes, now the last talk of the day, which is slightly longer, it's Shams Al-Mikowajek, and we're going to be talking about the CCD4 black hole dawn. So the third talk about the black hole dawn.
Okay, hello everybody. I'm Shams Mikowajek from University of Warsaw and University of Wrocław. I will be talking to you today about how to process your photometric observations through PHTOM. And at the beginning, I would like to acknowledge the work of other people on this, especially Zbigniew Kołaczkowski, who passed away 3 years ago and who was who began the work on the photometric and astrometric pipeline, as well as Paweł Zieliński, Krys Rybicki, Łukasz Wyrzykowski, Maja Jabłońska, and Piotr Ciąkowski. Okay, so let me start with what I will be speaking about today. I will just tell you what CCD4 is and how does it work, and later on we would go through processing your own observations through PHTOM. But before that, we will learn how to add your new instrument to PHTOM. Many of you also asked about the possibility to process multiple fixed files. So at the end, I will show you how to do that as well. So let's start with what CCD4 is. It is just a simple pipeline which utilizes widely available software, especially Sectractor at SCAMP, who was written by Bertin, and as well as DAOFOT, which was written by Stetson, but as you can see, many years ago. Still, some of the components of CCD4 are routines from IRAF and PIRAF, which we will try to move away from in the future. So the code is mainly written in Bash and Fortran, in Python as well as in Fortran. Here I outlined which of the components will go away in the future, being DAOFOT and IRAF-PIRAF, but we would like to introduce profile photometry with Sectractor. Now the PSFX component of the new Sectractor version is very well done, and the PSF photometry is quick enough to be incorporated into our pipeline. Right now, we still rely on DAOFOT because of the speed of the computation, but in the future, we will try to go to the new version of Sectractor as well. Of course, we use many free, open, and available tools like WCS tools, SI Clips, and CDS client, and so on. So we are not really making anything new, apart from the very good management of options available within this software. So how does the CCD fault work? So the input data is twofold. First are calibrated images. In the future, we will try to introduce some kind of automatic calibration, mainly for amateur astronomers who are not able to do it properly. This is very easy, but fixed calibration is very easy, but sometimes not updating your flat images may cause your later measurements to be unreliable. On the other input data is observatory site, telescope, and instrument information, which we simply call OPS file, OPS info file. And from these two input sources, we standardize fields file headers, and then we perform initial SCAMP and Sextractor astrometry. So the Sextractor finds sources in the image, and SCAMP matches those sources with catalogs like URAT1, UCAC4, and NOMAD1, which cover the entire sky, and then we get the coordinate grid. Then we download the list of stars from this field, from Gaia, right now it's Gaia EDA3, and validate the previously computed astrometry. If everything is okay, then we perform further calculations, starting with Sextractor photometry with Crowley aperture, then aperture photometry from Downfot, and finally profile photometry with Downfot as well. If everything goes right, then we can perform Gaia astrometry with much greater precision than the initial astrometry that we had in the beginning. CCD fault also prepares resulting files, and then these resulting files are being sent to BHTOM. And we adapted the Sextractor format to be the basic format for BHTOM. So here you have just a single raw frame from IST-60 observatory, which was added to BHTOM just a few days before our workshop. And in the left, you have just the field of stars, and the right, the feeds header as it is produced by the IST-60 software. So if you look at the image, it's not really well visible, but there are some artifacts from calibration visible somewhere here, which may or may not cause problems in the future. If our star of interest is somewhere close to these artifacts, the measurement will not be reliable at all. So that is the first problem that we can have with such frames. That's why we want to introduce automatic calibration. And at the right, you can see how the software performs all the calculations on this single frame. So it downloaded the field, the list of stars for this field, and it only happens once for given object. In the future, the software will use the same list of stars, significantly reducing time of computation. So as you can see, this frame was reduced, and here we can see the results. So first, we have standardized fields in the headers, which allow us to perform further calculations like astrometry and photometry. And here we have the coordinate grids and image with subtracted stars. As you can see, the PSF function wasn't calculated in the best way because of the poor seeing in the frame, as well as because of the poor calibration. And in the top of the image, you can see some black spots, which are also visible in a raw image, but the subtraction of the stars allows us to go into higher contrast and see such things in the image. So CCD produces three types of photometry. As I mentioned, first is sectracker photometry, second and third photometry types come from DAO-PHOT, which is aperture and profile. So sometimes it will happen that the profile photometry is not the best because of the poor PSF model, but CCD-PHOT will prepare the results for the best photometry in terms of error bars somewhere around your star's instrumental magnitude. Here you have another example of REM ROS2 instrument, and this is very poor image with a lot of calibration problems, but you can see that the PSF was performed very well, as well as the limiting magnitude of these calculations is somewhere about around 18 magnitude. So the software was constructed in a way to be able to process very sparse fields, averagely populated fields, as well as very dense stellar fields. So in the beginning, we had this huge problem with processing images from our observators, that they put different object names in the feeds headers, which then couldn't be recognized properly by our software. So right now we are introducing the coherent method to just the independent method to just use object name from BHTOM and then apply it to feeds headers and use that for further processing. As well as we will be adding new databases to resolve object names and coordinates from. So this is no longer a problem. It no longer will be a problem at the end of this month. This option is now right now at the testing phase. Here's some examples of subtracted fields of stars for sparse and very dense fields. As you can see, even you have a very bright nebula, the subtraction goes very well. Here is actually the same object with, here we have R filter with nebula visible, and here I filter with invisible nebula, and the subtraction of stars is so good that you can clearly see that the only thing visible in the subtracted image is just fringing. And here the object known by all of you, so Gaia 16 AYE or Ayers Rock, with stars subtracted, and over 14,000 sources were subtracted from this image. If we really tried, we could probably find some 1,000 stars more here in this image. Okay, so knowing how the CCD-PHOT works, let's try to add a new observatory in BHTOM. So if we go to BHTOM Astrolabs PL, just click on observatories, and if you want to add your instrument, which already is in our database, just click on add new observatory. I have all but one observatories added. So when I go to the add observatory, I have only one available from scroll down list. So I choose the available observatory and I add it to my list. After you do it, you will be informed that it was successfully created, and then it will appear in your observatory list. You will be assigned a custom hashtag, which will consist of this prefix, which we generate for each observatory, and it is for each observatory and instrument is different. Then it will be a login and a string of letters and numbers, just to make sure that no one has the same. The true column means that this observatory is active in the BHTOM system and you can process your feeds files. If it's not active, if it says false, we still are working on activating it. We are testing the data that we got from observers. You can edit your observatory anytime you want and give it a custom name for you to know which observatory it is. Because we try to name it so there would be no duplicates, but you can just name it with the name that you that you want. Of course, you can always delete your observatory if you're not uploading any data from it anymore. So let's say that as in my case, I have no more observatories to add to my list, or you just want to create your own observatory, you just want to upload data from your own telescope. So then as you can see, I had one observatory in my list, I added it, and it disappeared, so I just have to create new observatory, clicking here in the bottom. When you do it, you will see a really simple form that probably takes 5 minutes to fill in. So you start with this observatory name. You can just type anything you want here, so you know what it is, just maybe a place of the observatory, type of telescope, and maybe some designation for CCD camera. We will then later generate this complicated string, which also will tell us what it is. Then you have to put longitude, latitude, and altitude of your observatory. And we decided that we would just take west as positive. So please make some calculations if you have to. Then matching radius means that sometimes when you have a really sparse field, it's better to give a bigger matching radius, but in case of adding your observatory here, two arc minutes is just fine. Or maybe if you have a really large field of view, please try to divide your field of view by 10 and then put the matching radius like that here. You can also stand here that you only want to upload on instrumental photometry file, so you will not be uploading feeds files, but we strongly encourage you to not do this, to give us your feeds files to process with CCD photo. So after you go with this, you please provide as many simple feeds files as you can, preferably 1 or 2 in each band, and preferably for different objects. This will help us to really quickly perform tests and avoid problems in the future. Please provide gain, beaming, saturation level for your CCD camera, and if you want to add different camera modes, just create a new observatory. In the future, we think about having a possibility to add camera modes in this form independently. Please provide your pixel scale in arcseconds per pixel and your readout speeds for the camera. The readout speeds is not really that important because it doesn't take, we don't care about it during the calculations, but it can say us something about how you perform your observations. If your readout speed is too high, it probably means that you can go down with it and have lower readout noise, which will contribute to lower magnitude error in the future. So for us, it's also information to give you feedback what not to do during your observation. And pixel size for your camera, as well as approximate limiting magnitude for your telescope. And this may be hard to assess, especially for amateur astronomers. So just simply put a number, a magnitude of an object that you can see, let's say, with an exposition of 5 minutes in V band or G band of Sloan's system. Okay, when we are at with filters, so please provide just the filters that you have in your observatory, but as they are seen in your feeds headers. Sometimes it happens that we have to rewrite those names to more, let's say, common names of filters. Here you have a simple example of VAT instrument on Vatican telescope, which has 2 filter wheels, and those top and bottom positions correspond to PS, U, and V filters. So sometimes you can just put R. Johnson in your feeds header, and we will rewrite it to R. So that is not a problem, but please state the filters as they are seen in your files. And at the last, you can put some comments in the comments section. Here I created the observatory for Skinaka's icon L imaging camera, and I put under web page and Skinaka's web page to provide us with this simple link to the database that we can check out ourselves. Of course, you can also paste as much comment as you want. You can say that maybe your camera is saturating at 63,000 ADUs, but the linearity ends at 50,000. This is also an important information that we would like to know. The more you provide us, the quicker we will activate your observatory. So then you click Create Observatory. You should be informed that all is well. And what we get from this, our software will create this ops info file that I mentioned in the beginning. So last year we tried to teach you how to fill in this file yourself, but it is really complicated, and really we had a good effect with this. So better way was just to create this simple form for you to provide us information, and our software will create the form itself. Here you have the form for one of the observatories in our system, and we have all this information visible in our proprietary OpsInfo file. Okay, so what happens next? After you create an observatory, BHTOM emails us or itself, and it takes about a week for us to perform tests and activate your observatory. Of course, if you provide us very good information and a lot of FITS files, it may take 6 hours, depending on our availability at the time as well. So let's assume that all is well, and now we can process an image with BHTOM. So just go to any object that you want, any target in BHTOM that you want, and click on the upload at the top. When you do it, this page will appear, as Pavel was telling you as well yesterday, and you will be asked to choose a file, or we can choose multiple FITS files here as well. So there were some questions whether you can upload multiple files with a web page. Yes, you can do that. If you have like 5 images per night, it's a good idea to do this way. But please do not upload more than 5, let's say, or 10. Because if you do this, we will have our system stuck, and then we have some additional problems that we have to resolve. I will show you in the next step how to upload multiple FITS images with simple Python script. So let's say that I have already chosen a FITS file, and here you have the example from Josh Ham's observatory, who had a wonderful talk today. And you choose FITS image for automatic processing and observatory from the scroll down list that is adjacent to the FITS file that you have just chosen. You can also choose dry run if you're not sure that photometric processing will go well for your upload. But do it just once. If all is well, then the subsequent uploads just don't use dry runs. All should be fine. So if you just do this, in the next step, at the bottom of the page, you can click upload. When you do it, you will be informed again that all is well. If you upload multiple files, then file names will be here listed. All file names will be listed here. And you will be informed that your file is not processing, and this might take several minutes. In case of really large field of views, we will perform cut only 30 by 30 minutes field of view. So if you have Schmidt camera with 1 degree, we will cut the image not to give our pipeline too many things to do, and let other people process their images as well. In case of really crowded fields, 30 by 30 minutes is more than enough to find a sufficient PSF model to subtract stars and perform PSF photometry. Okay, so when you upload your file, then you can click on data, and you will see all the files, not only feeds, but also instrumental photometry files that have been uploaded so far. Sometimes you can see photometry errors, and in this case, you can see in this slide, I uploaded Josh's Hampshire files and chosen the wrong observatory. So it was my bad. I got photometry error, of course. But if you click on your files, then you can see only files that you uploaded. And here is one of the files out. This exact file I uploaded for this presentation. And you can click on detail and find out what happened with it subsequently. The dry run here is active, but all the photometrics processing have been done, as well as the calibration to standard magnitude, but the photometric point will not appear in calibration server, will not appear in the graphs in BHTOM as well. So if it is fine, then you can unselect dry run and upload your files. Okay. So what if you have multiple images, or hundreds or thousands of them? So then the thing that was programmed by Maja Jabłońska and Piotr Ciąkowski is now available for you at GitHub. Also, I created this shorter URL for you to write down, or later when you'll be watching the video from conference, you can use it. But probably we will just link it at our page somewhere for you to download. This is a really easy script visible here, and I will just go through this very quickly. The latter part is not important. The most important is in the beginning. You have to specify your directory where your feed files are. You have to specify the target as it is seen in BHTOM site, as well as your hashtag generated previously while adding new observatory to your list. If you have this, you have to specify filter. This is not so easy, so just put auto for automatic filter selection. Unless you know that your photometric system is not very standard, then try to put some kind of photometric filter here for us to try to calibrate to standard magnitude. Then data product type is just feeds file. We'll probably in the future make available also uploading instrumental photometry as well here. And for dry run, you can just put true or false, whether you want it to be a photometric point in our database on just for some trial. And then the video from Piotr is, you can see here what happens when the script is run. It was several files from Gaia 18 DIF, and this video was a little bit sped up. And after each of these processing, a photometric point should appear in our database, and it will. So let's wrap up. Two things left. What we are working right now in our team is developing new version of the pipeline. So far, the CCD fault was just a linear procedure which had to go from the beginning till the end. Now it will be broken up into three parts: CCD Astro, CCD Photo, and CCD Gas. And sometimes it is sufficient to just process the file with CCD Astro, because it will provide a very good astrometric solution and sextractor photometry. If this is good enough, then it will be processed by CCD Photo. So this is just PSF photometry with DAO and in the future with sextractor. And if this is good enough, then we can go to the Gaia astrometric solution for very precise astrometry and write this astrometry to feeds headers. We are going to speed up data processing in the future, as well as move away from IRAF, PIRAF, and some data of. We are developing new routines for profile photometry and scripting data upload to BHTOM, which Maja and Piotr are working on right now, and along with this automatic object name resolving, it should be available for you at the late November, early December. And we are preparing documentation and manuals and probably some video manuals also from this workshop. And here you have the, all the instruments that were available in our database at the time of last conference, last January. It was 26 instruments and 2 were in the process of testing. Right now we have 40 instruments and 4 are pending. The first one is at the Yaman 60 centimeters telescope in Turkey. So please register your telescopes in BHTOM, create new observatories, supply us with test feeds files, and maybe at the during the time of the next conference we will maybe go to 100, hopefully maybe 60, 80. Let's see. If you have any questions, now is the time. Thank you.
There are some questions on the chat. So does it run on Windows 10 as well?
This is the default.
No, I think it's about the upload.
No, upload is just a Python script. So as long as you have Python in your system, it will work from the level of Mac, Windows, or Linux. It doesn't matter.
Yeah, I hope this answered the question correctly. And if not, you can unmute yourself and ask Josh.
Hi. I mean, I don't have Python on my PC. I don't use Python.
Okay, so if you do not have Python, maybe we will think of something in the future.
An executable should be okay.
Yeah, it can be done. Python can be in a way compiled down to binary files, so maybe we can work something out for Windows as well.
Thank you.
You're welcome.
Next question from Michel.
Yes, I have a question about the photometry, because I have been working all the time with Cousin's filter at Haute-Provence, and in the system, when I state I have a Cousin's filter, the system is not able to give photometry. It says it cannot. If I put any R-band filter, sometimes it works, sometimes it does not, and if I put automatic, it gives a PS1 filter or a gun filter, and so what is the photometry reliable or not? You know?
Yeah, this is a question more to Paweł and Łukasz, I guess, because CCD4 is not providing a standard photometry. It only provides instrumental photometry, and then this photometry is being transformed to differential photometry, and that differential photometry is standardized then with 0-point correction and the future color term correction as well. This is a no problem for us, and we are working on fixing it, because sometimes it really happens that you have standard R Cousins filter and your point cannot be standardized. It can be of 2 reasons. One is we have problems with our database, and we had such in the past. And the other is, in the field of view, there are just no standard stars to properly calibrate the observation. So there are some new surveys like DECAPS or PAN stars still being updated. We will introduce other surveys in the future, so probably within some reasonable window of time, we will be able to fix those problems altogether.
Yeah, but it means if your data are transformed into whatever PS1 or gun magnitudes, how are they reliable? Because there are color terms between the different systems. You know?
Exactly, that's what we are working on right now. But this question doesn't really isn't really about the photometric processing, because I can subtract stars from any image, and I don't really care what filter it is. This is not. This is just a numerical procedure, and the standardization comes after that. So maybe you can contact, I think, Paweł and Łukasz and not as well, no? Paweł and Łukasz for them to elaborate on that.
Yeah, well, as Przemek said, we are working on this. This is important, but for us at this very moment, these how to put it, the systematics introduced by the fact that we don't correct for the color are small enough, let's say, that the data is already usable. Of course, if we want to improve the accuracy of the photometry, then we will include this effect into processing. But this will be done, don't worry.
Yeah, we also add that huge chunk of the magnitude error that you can see in the CPCS or BH-TOM comes from the standardization. So the magnitude error from instrumental photometry may be like at the level of millimagnitude, and then it becomes much more after the standardization. If we introduce all this procedure correctly, then we should be able to go down with this error back to instrumental magnitude or something like this.
Okay, thank you.
Okay, a question from Rupak. I'm not sure.
Am I audible? Yeah. So is there any plan to implement this image subtraction routine and BH-TOM in future?
Image subtraction. Because now we do the PSF profile photometry. Rupak working on supernovae, I guess. He's interested in difference imaging.
Oh yeah. I am currently working on two different image subtraction methods. First is morphology introduced by Bertin in his newer sextractor version. So this will be put in place instead of day of hot. But also different image analysis is possible. We will introduce it in the future for sure. And then we will differentiate between different methods based on the stellar density in the field, based on the galactic latitude maybe. And different methods can be used for different objects just to provide us as good subtractions of stars as we can.
Okay. Thank you.
Okay. Also, Secret has a question.
Yes, can you please share the link to the Python script for uploading on Slack?
Yeah. And Justas?
Yes, you show how to create a new instrument for a telescope.
Yes.
But we need sometimes change this data. How to change them?
So this is if you want to change your data, it means maybe that you are adding new filters, right?
Yeah.
Yeah. So then just it would be easy. The easiest to delete the observatory and add it again. We will develop methods to edit, but it's not that easy because let's say that you have a set of filters, standard Johnson-Cousin filters at 10 observatories. The entries in the feed headers are different everywhere. One will put just V, another one will put V Johnson, and so on. So it doesn't really solve the problem. If you are adding new filter, it would be just the easiest method to just email us with new entries in your feed headers, and we can substitute in our system within 20 minutes. So it is really easy. As long as you are not changing filters every other week, so that would be really
yeah, because matter observatory way changing this table, wheel 1, wheel 2, and filter can be every month different.
Yeah, so just add 2 observatories. It will mean that you have 2 different, because in essence you have 2 different instruments.
And I can show how I can show what is in exact observatories parameter. Is it possible to look what parameter?
What do you mean?
I think what it means is that the observatory
in this observatory it is
Exist, yes. If I have yes, if I have two the same observatories and I need one of them the same branches that I need, then I found which is used for me.
Yeah, you put your own observatory name that you want. You can just say first my observatory with the first set of filters, my observatory with the second set of filters. We will assign different hashtags to them, and you will just upload when you upload your data, you will choose the one you want, and that's.
But after, if I don't know, I can't so.
But if you don't know, then you cannot upload your data.
Well, let me comment on this.
Just look what parameter was uploading.
Yeah, it's a very good comment it's like a feature request because we ask you for a lot of information and then we have access to this, but you don't. That's a good point. We will write it down. So when I list the observatories, I should be able to see, for example, the OPS info file, like this.
Yeah.
So people can look what they actually put in there.
Yeah,
that's a good idea. Wrote it down.
I think that if you also log into your PH-Tone, you can do something like this already, no?
No.
Okay. So maybe we should just add a hyperlink to download this OPS info file for each observatory that you add to your list. And then you can go inside and look what filters have been defined in this particular observatory. And I hope this solves your problem.
You can definitely add a details tab when you show all these fields you mean when adding file in the form. So that's going to be relevant.
Yeah, that would be even quicker, not to download the file, just to go with details, and then you will be shown what filters are assigned to your observatory, and you can just check it every time you upload your data.
Yes, this won't have all of the information because OPS info is more detailed than just the form, but for basic things such as filters and reading, the stuff from the form will be there.
Yeah.
So we will add that.
So we will do it. We are in the process of editing this part of VH-Tone right now. So thank you for this because we will provide it right now, I guess.
Yes.
In the next update, we will do it.
Just after the conference dinner, you will see.
Yes, or even before. Pavel will be working on that, so it's probably before the dinner.
Yeah. Okay, so this is I think for the time. Thank you again for the talk.
Thank you.
This is great, and for all the future discussions, let's ask them there so that we have them there forever. And let's thank all the speakers again.